It's almost impossible to believe, but hidden in the vast darkness of space are objects so strange, so baffling, that even the most advanced minds in astronomy are left scratching their heads. Imagine two stars locked in a cosmic dance, one of them a dead remnant of its former self, yet capable of unleashing astonishingly powerful bursts of energy. The other is a seemingly ordinary star, yet it's being drained, slowly but surely, by its partner. Now add a twist. The dead star has an insanely strong magnetic field that bends, distorts, and controls the flow of matter, creating mesmerizing patterns of chaos. These systems are called polars and intermediate polars, and their behavior is as mysterious as it is captivating. But before we continue, subscribe to the channel so you don't miss out on any of these videos. At first glance, these binary systems might not seem all that different from other white dwarf binaries. After all, white dwarfs, remnants of stars that have exhausted their nuclear fuel, are fairly common in the universe. But polars and intermediate polars belong to a special class of systems where the rules of astrophysics are bent, sometimes almost to the breaking point. Their story is one of magnetism, accretion, and energy, forces that combine to create some of the most extraordinary phenomena ever observed in the cosmos. What makes these systems so strange? It's the white dwarf's magnetic field. In most binary systems, when a white dwarf pulls material off its companion star, the matter forms a spiraling accretion disk around the white dwarf. But in polars and intermediate polars, the magnetic field is so intense that it disrupts this process. Instead of forming a disk, the material gets funneled along magnetic field lines, crashing directly onto the white dwarf's surface at specific points. These hot spots are where the magic happens. They emit powerful X-rays and other forms of radiation, lighting up the system in ways that can be detected across vast cosmic distances. But let's break this down further. Polars, sometimes referred to as Amher stars, named after the prototype system, Am Hercules, are the extreme cases. Their magnetic fields are so strong, often tens of millions of times stronger than Earth's, that they completely dominate the behavior of the system. The white dwarf's magnetic poles act like a gigantic cosmic vacuum cleaner, pulling material directly from the donor star and channeling it along magnetic field lines. The accretion process in polars is incredibly efficient, releasing massive amounts of energy as the material slams into the white dwarf's surface. Intermediate polars, on the other hand, are a bit less intense. Their magnetic fields are strong, but not strong enough to completely eliminate the accretion disk. Instead, they create a hybrid system where some of the material still forms a disk, but part of it gets channeled along magnetic field lines. These systems are also known as DQ-Her stars, after another well-known example, DQ Hercules. The dual nature of intermediate polars, part disk, part magnetic funnel, makes them even more puzzling and fascinating to astronomers. Now, here's where things get really intriguing. The behavior of polars and intermediate polars isn't just a result of their magnetic fields. It's also influenced by the interaction between the two stars in the system. The donor star, often a low-mass main sequence star, is being slowly stripped of its material by the white dwarf. This material transfer creates a delicate balance of forces, and even small changes in the system can lead to dramatic shifts in behavior. For example, changes in the rate of accretion can cause the system to switch between periods of high and low activity, a phenomenon that astronomers are still trying to fully understand. Another mystery lies in the rotation of the white dwarf. In polars, the magnetic field is so strong that it locks the white dwarf's rotation to the orbital period of the binary system, a state known as synchronous rotation. This means the white dwarf always presents the same face to its companion star, much like the moon always shows the same face to Earth. But in intermediate polars, the rotation is asynchronous. The white dwarf spins faster than the orbital period. This creates a fascinating interplay of magnetic and gravitational forces, leading to complex and highly variable emission patterns. The emissions from these systems are another area of active research. The hot spots on the white dwarf's surface, where the accreted material crashes down, are incredibly energetic. They produce intense X-rays, ultraviolet light, and visible light, making these systems some of the brightest objects in the sky at certain wavelengths. By studying these emissions, astronomers can learn a great deal about the physics of accretion and the properties of the white dwarf and its magnetic field. But there's still so much we don't know. For example, why do some white dwarfs develop such strong magnetic fields in the first place? And why do some systems become polars while others become intermediate polars? These questions remain unanswered, and they highlight just how little we understand about the complex interplay of forces in these systems. Polars and intermediate polars also have a unique role to play in the broader context of astrophysics. They serve as natural laboratories for studying extreme magnetic fields, accretion processes, and binary star evolution. They also provide important clues about the end stages of stellar evolution and the fate of binary systems. In many ways, they are the cosmic equivalents of crime scenes, with astronomers playing the role of detectives, piecing together clues to understand what happened and why. The more we study these systems, the more mysteries we uncover. For instance, some polars exhibit what's known as low states, periods when the accretion rate drops dramatically, causing the system to dim significantly. What triggers these low states? Is it changes in the magnetic field, the donor star, or something else entirely? Similarly, some intermediate polars show unusual variability in their emissions, suggesting that their magnetic fields may be more complex than we thought. Then there's the question of how these systems evolve over time. As the white dwarf continues to accrete material from its companion, its mass increases. If it reaches a critical limit known as the Chandrasekhar limit, about 1.4 times the mass of the Sun, it could trigger a catastrophic supernova explosion. Alternatively, the system might evolve into a different type of binary altogether, such as a neutron star or black hole binary. Understanding these evolutionary pathways is crucial for building a complete picture of stellar evolution. Polars and intermediate polars also have broader implications for our understanding of the universe. Their emissions can serve as beacons, helping astronomers map the distribution of binary systems in our galaxy. They can also shed light on the role of magnetic fields in shaping the behavior of stars and other cosmic objects. And because they are relatively close to us in astronomical terms, they provide an excellent opportunity to study these phenomena in detail. The mysteries surrounding polars and intermediate polars only deepen as we uncover more about their behavior. For example, one particularly fascinating aspect is the nature of their magnetic fields. In polars, the magnetic field is often measured in the range of tens to hundreds of megagauss, an incomprehensibly strong force. To put that into perspective, the strongest magnets humans have created in laboratories produce fields in the tens of teslas, and a megagauss is about 100,000 teslas. This immense magnetic field has a profound effect on how matter is funneled onto the white dwarf's surface, effectively creating magnetic tunnels that direct plasma with pinpoint precision. In intermediate polars, the magnetic field is weaker, though still staggeringly strong, and this creates a hybrid behavior. The interplay between the residual accretion disk and the magnetic funneling creates a complex, dynamic system. Unlike polars, where the magnetic field completely dominates the flow of matter, intermediate polars display characteristics of both disk-fed and magnetically channeled accretion. This makes them ideal targets for studying the transitional behavior of accreting white dwarfs under varying magnetic conditions. One of the defining features of these systems is their variability. The emissions from polars and intermediate polars often vary on multiple timescales, from seconds to hours to days. This variability is primarily driven by the rotation of the white dwarf and the orbital motion of the binary system. In polars, the synchronous rotation means that the hotspots on the white dwarf's surface rotate in lockstep with the orbital period. This produces a highly regular pattern of variability, with the system brightening and dimming as the hotspots come into and out of view. Intermediate polars, with their asynchronous rotation, exhibit a more complex pattern of variability, as the rotation of the white dwarf introduces additional periodic signals. These periodic signals are not just fascinating curiosities, they are also incredibly valuable tools for astronomers. By analyzing the timing and intensity of these signals, researchers can infer critical properties of the system, such as the strength and geometry of the magnetic field, the mass and radius of the white dwarf, and the structure of the accretion flow. These observations provide a unique window into the extreme environments around white dwarfs, where matter is subjected to conditions that are impossible to replicate on Earth. Another layer of intrigue comes from the so-called cyclotron radiation emitted by polars. As the accreted material spirals along the magnetic field lines, it emits radiation at specific frequencies determined by the strength of the magnetic field. This cyclotron radiation produces distinctive spectral features that can be used to measure the magnetic field strength and study the properties of the accreted material. In intermediate polars, cyclotron radiation is less prominent, but other emission mechanisms, such as Bremsstrahlung and thermal radiation, dominate, adding to the complexity of their spectra. One particularly puzzling aspect of polars and intermediate polars is their low states, periods when the accretion rate drops dramatically. During these phases, the system becomes much fainter, and the emission from the accretion hotspots diminishes or disappears entirely. The cause of these low states is not fully understood, but several hypotheses have been proposed. One possibility is that changes in the mass transfer rate from the donor star, perhaps driven by stellar activity or magnetic cycles, could temporarily reduce the flow of material onto the white dwarf. Another possibility is that changes in the configuration of the magnetic field could alter the accretion flow, leading to a temporary shutdown of the hotspots. These low states also raise intriguing questions about the long-term evolution of polars and intermediate polars. Are these systems in a stable equilibrium, or are they constantly evolving, with their magnetic fields weakening or strengthening over time? How do these systems transition from one state to another, and what triggers these transitions? Understanding these processes is crucial for building a complete picture of the life cycles of binary systems and the role of magnetic fields in shaping their behavior. The study of polars and intermediate polars also has broader implications for our understanding of astrophysics. These systems are natural laboratories for studying the interaction between matter, radiation, and magnetic fields under extreme conditions. They provide insights into the physics of accretion, the behavior of plasma and strong magnetic fields, and the mechanisms that produce high-energy radiation. They also offer a glimpse into the end stages of stellar evolution, showing how stars can continue to interact and evolve even after they have exhausted their nuclear fuel. Moreover, the emissions from polars and intermediate polars have practical applications in astronomy. Their intense X-ray and ultraviolet radiation make them valuable targets for space-based observatories, which can study their emissions in detail. These systems also serve as standard candles for measuring distances in the galaxy, as their brightness and variability can be used to estimate their distance from Earth. But perhaps the most tantalizing aspect of polars and intermediate polars is the sheer mystery that still surrounds them. Despite decades of study, we are still far from fully understanding these systems. New observations continue to reveal unexpected behaviors and phenomena, challenging our theories and pushing the boundaries of our knowledge. For example, recent discoveries of polars with unusually strong magnetic fields, or intermediate polars with highly irregular variability, suggest that these systems are even more diverse and complex than we thought. One exciting avenue of research is the use of next-generation telescopes and observatories to study these systems in greater detail. Instruments like the James Webb Space Telescope, with its unprecedented sensitivity and resolution, could provide new insights into the structure and behavior of polars and intermediate polars. Similarly, advances in computational modeling and simulation are allowing researchers to create more accurate and detailed models of these systems, helping to unravel their mysteries and refine our understanding of their physics. As we continue to study polars and intermediate polars, one thing is clear: these systems are not just curiosities of astrophysics. They are windows into the fundamental processes that govern the universe. They challenge our assumptions, inspire new questions, and remind us of the incredible complexity and beauty of the cosmos. The strange behavior of polars and intermediate polars is a compelling reminder of how much we still don't understand about the universe. Every new discovery about these binary systems reveals more layers of complexity, from their magnetic interactions to their peculiar emissions. This complexity is not just a challenge for researchers but also an opportunity to learn about fundamental astrophysical principles in environments that push matter and energy to their limits. One area where our understanding is still evolving is the role of the donor star in these systems. In both polars and intermediate polars, the donor star is typically a late-type star, such as a red dwarf, that is losing material to the white dwarf through processes like Roche lobe overflow. However, the rate at which this material is transferred can vary significantly over time. Some theories suggest that the donor star's activity, such as star spots, flares, or magnetic cycles, could influence the transfer rate, leading to fluctuations in the brightness and behavior of the system. Observing and modeling these interactions are key to understanding how the donor star contributes to the dynamics of these binary systems. Interestingly, the transfer of material is not a one-way street. In some cases, the intense radiation and magnetic fields from the white dwarf can influence the donor star, causing changes in its structure or activity. For instance, the intense X-rays emitted by the white dwarf can heat the surface of the donor star facing the white dwarf, creating a hot spot that is much brighter than the rest of the star. This feedback loop between the two stars adds another layer of complexity to these systems, making them even more fascinating to study. The accretion process itself is a highly dynamic and turbulent phenomenon. In polars, where the magnetic field dominates, the material flows directly along the magnetic field lines and impacts the white dwarf's surface at the magnetic poles. This creates accretion hotspots that are incredibly bright and emit radiation across a wide range of wavelengths, from X-rays to optical light. These hotspots are also sites of intense energy release, with temperatures reaching millions of degrees Kelvin. Studying these hotspots provides valuable insights into the physics of high-energy processes, such as shock waves, particle acceleration, and radiative cooling. In intermediate polars, the accretion process is even more complex. Because the magnetic field is weaker, the material initially forms an accretion disk around the white dwarf before being funneled onto its surface by the magnetic field. This creates a unique hybrid structure where the disk and the magnetic field interact in intricate ways. The disk can become warped or tilted due to the influence of the magnetic field, and instabilities in the disk can create periodic outbursts or flickering. These phenomena are not just intriguing to observe but also provide valuable data for testing theories of disk accretion and magnetohydrodynamics. One of the most fascinating aspects of polars and intermediate polars is their ability to produce polarized light. In polars, the intense magnetic field causes the emitted light to become polarized as it interacts with the accreted material. This polarization can be measured and analyzed to determine the properties of the magnetic field, such as its strength and orientation. In intermediate polars, polarization is less pronounced but can still provide useful information about the system. Polarimetric studies of these systems have revealed unexpected behaviors, such as rapid changes in polarization that may be linked to changes in the accretion flow or the magnetic field. Another intriguing feature of these systems is their potential to produce gravitational waves. As the white dwarf and the donor star orbit each other, they create ripples in spacetime known as gravitational waves. While these waves are much weaker than those produced by more massive systems like neutron star mergers, they are still detectable with sensitive instruments like LISA, Laser Interferometer Space Antenna, which is scheduled to launch in the coming years. Detecting gravitational waves from polars and intermediate polars would not only confirm their existence but also provide new insights into their orbital dynamics and mass distribution. The study of polars and intermediate polars also has implications for understanding the end stages of stellar evolution. White dwarfs are the remnants of stars that have exhausted their nuclear fuel, and their behavior in binary systems can provide clues about the processes that occur during and after the death of a star. For example, the intense magnetic fields in polars and intermediate polars may be remnants of the magnetic fields of the progenitor stars, preserved and amplified during the collapse into a white dwarf. Understanding how these fields evolve over time can shed light on the life cycles of stars and the role of magnetic fields in shaping their destinies. One of the most exciting frontiers in the study of these systems is the search for unusual, or extreme examples. For instance, astronomers have discovered polars with magnetic fields so strong that they completely disrupt the accretion flow, creating unique emission patterns. Similarly, some intermediate polars have been found to have unusually high accretion rates, suggesting that they may be in a temporary phase of rapid mass transfer. These extreme cases challenge our models and provide valuable opportunities to test our understanding of the underlying physics. As observational technology continues to improve, we are likely to uncover even more surprises about polars and intermediate polars. Instruments like the Extremely Large Telescope, ELT, and next-generation X-ray observatories will allow us to study these systems in unprecedented detail, revealing new aspects of their behavior and interactions. At the same time, advances in computational modeling and simulation will enable researchers to create more realistic and detailed models of these systems, helping to explain their complex behaviors and predict new phenomena. The mysteries of polars and intermediate polars are far from solved, but each new discovery brings us closer to understanding these enigmatic systems. They remind us of the incredible diversity and complexity of the universe and the endless possibilities for exploration and discovery. As we continue to study these systems, we are not just learning about the stars and their interactions, we are also gaining deeper insights into the fundamental laws that govern the cosmos and our place within it. The ongoing exploration of polars and intermediate polars showcases the incredible complexity of binary systems. One of the most captivating aspects of their study lies in the variety of behaviors these systems can exhibit, which often defy expectations and provide critical tests for astrophysical theories. Let's delve even deeper into some of the most remarkable discoveries and questions surrounding these systems, which continue to fuel curiosity and investigation. For starters, one question that astronomers are eager to answer is how the strong magnetic fields in polars and intermediate polars are maintained over time. Magnetic fields in white dwarfs are thought to be relics of the stars they once were, inherited from their progenitors during the stellar evolution process. However, the strength and structure of these fields can vary significantly from system to system. Some theories suggest that these fields may decay over millions of years, while others propose mechanisms by which they could be sustained or even amplified through interactions with the accreting material. Observing systems at different evolutionary stages can provide clues, but a definitive answer remains elusive. In polars, where the white dwarf's magnetic field dominates the accretion process, the strong field lines completely channel the infalling material, forming accretion columns that funnel plasma directly onto the magnetic poles. This direct accretion process generates enormous amounts of energy, which is released as X-rays, ultraviolet light, and polarized optical emissions. These emissions often exhibit cyclical patterns corresponding to the rotation of the white dwarf, offering a unique window into the system's dynamics. One of the most intriguing phenomena observed in polars is cyclotron radiation. This occurs when charged particles spiral along the magnetic field lines at relativistic speeds, producing radiation at specific wavelengths. The resulting emission lines are highly polarized and provide detailed information about the magnetic field's strength and structure. By studying these emissions, astronomers can reconstruct the magnetic geometry of the white dwarf and gain insights into how magnetic fields influence accretion processes. Cyclotron radiation also serves as a diagnostic tool for understanding the physical conditions in the accretion flow, such as temperature, density, and velocity. Intermediate polars, on the other hand, offer a fascinating blend of disk accretion and magnetic control. These systems are characterized by their weaker magnetic fields, which allow the formation of an accretion disk around the white dwarf. However, the inner regions of the disk are disrupted by the magnetic field, which channels material onto the white dwarf's surface. This creates a dual-layered accretion structure, with both disk and magnetically channeled flows coexisting. One of the defining features of intermediate polars is their rapid spin periods. Unlike polars, where the white dwarf's spin is synchronized with its orbital period, intermediate polars often have spin periods that are much shorter, ranging from a few seconds to several minutes. This discrepancy arises because the weaker magnetic field is insufficient to lock the white dwarf's spin to the orbit of the donor star. Instead, the system exists in a state of partial synchronization, where the spin and orbital periods are related but not identical. This leads to complex, time-variable emission patterns that can reveal details about the accretion process and the system's evolution. The accretion disks in intermediate polars are also prone to instabilities, which can trigger dramatic outbursts or flickering events. These fluctuations in brightness are often linked to changes in the rate or structure of accretion. For instance, a sudden increase in the mass transfer rate from the donor star can temporarily overwhelm the disk, causing it to brighten significantly before stabilizing again. These events are not only visually striking but also provide valuable data for testing models of disk dynamics and accretion physics. Another aspect of intermediate polars that has drawn considerable attention is their X-ray variability. The combination of disk accretion and magnetic channeling creates a unique X-ray signature that varies over time due to the rotation of the white dwarf and the precession of the disk. These variations often occur on multiple timescales, reflecting the complex interplay of processes within the system. By analyzing X-ray light curves, astronomers can disentangle these contributions and gain insights into the geometry and dynamics of the accretion flow. Both polars and intermediate polars are also fascinating laboratories for studying the effects of magnetic fields on plasma physics. The intense magnetic fields in these systems create conditions that are difficult to replicate on Earth, such as extremely high temperatures, densities, and magnetic pressures. Observing how matter behaves in these environments can provide valuable insights into fundamental plasma processes, such as magnetohydrodynamic instabilities, magnetic reconnection, and shock wave formation. Moreover, the strong magnetic fields in polars and intermediate polars have implications for the long-term evolution of these systems. For instance, the intense magnetic torque exerted by the white dwarf can transfer angular momentum from the binary orbit to the white dwarf's spin, gradually altering the orbital separation and period. Over time, this can lead to significant changes in the system's configuration, potentially driving it toward a merger or a new evolutionary phase. Understanding these processes is crucial for predicting the future behavior of these systems and their role in the broader context of binary star evolution. Another area of active research is the potential connection between polars, intermediate polars, and other types of compact binary systems. For example, some theories suggest that intermediate polars could evolve into polars as their magnetic fields strengthen over time. Alternatively, polars could transition into intermediate polars if their magnetic fields weaken or their accretion rates change. Observing systems at different stages of evolution and comparing their properties can help test these hypotheses and refine our understanding of the evolutionary pathways of magnetic binaries. The diversity of behaviors observed in polars and intermediate polars also raises questions about the broader population of such systems. How many of these systems exist in the galaxy? What factors determine their magnetic field strengths, accretion rates, and emission characteristics? And how do they contribute to the overall population of cataclysmic variables and binary systems? Surveys using instruments like Gaia, which can detect faint and distant objects, are helping to address these questions by identifying new systems and expanding our understanding of their distribution and properties. In addition to their astrophysical significance, polars and intermediate polars are also intriguing from a philosophical perspective. They challenge our intuition about how stars and matter behave, offering a glimpse into the extreme conditions that exist in the universe. They remind us of the interconnectedness of physical processes, where magnetic fields, gravity, radiation, and plasma dynamics all come together to create phenomena that are both beautiful and complex. The mysteries surrounding polars and intermediate polars extend beyond just their mechanics and dynamics. These systems have implications for broader astrophysical phenomena, including the formation of white dwarfs, the role of magnetic fields in stellar evolution, and the eventual fate of binary star systems. By diving deeper into their intricacies, we gain not only a more profound understanding of their unique behaviors but also insights into the fundamental workings of the cosmos. One of the most compelling aspects of these systems is their potential connection to the ultimate fate of white dwarfs. When a white dwarf in a binary system accrues enough mass from its companion, it may approach the Chandrasekhar limit, a critical mass of about 1.4 times the mass of the Sun. Beyond this limit, the white dwarf can no longer support itself against gravitational collapse, leading to either a Type I supernova or the formation of a neutron star. Polars and intermediate polars, being prime examples of systems where mass transfer is actively occurring, provide valuable case studies for understanding how white dwarfs evolve toward these dramatic endpoints. In polars, the direct accretion of material onto the magnetic poles can create hotspots that emit intense radiation. These hotspots not only reveal the current state of the accretion process, but also serve as a record of the material being transferred from the companion star. By analyzing the composition of the radiation emitted from these regions, astronomers can infer the chemical makeup of the accreting material. This can shed light on the evolutionary history of the donor star and the white dwarf itself. Intermediate polars, with their partially synchronized accretion processes, offer an even more dynamic picture. The interaction between the accretion disk and the magnetic field can create instabilities that manifest as quasi-periodic oscillations, QPOs. These oscillations, which occur on timescales of seconds to minutes, are thought to result from the interaction between the magnetic truncation radius and the inner edge of the accretion disk. Observing and modeling these QPOs can provide critical insights into the coupling between magnetic fields and accretion flows, as well as the conditions in the innermost regions of the disk. Additionally, the study of polars and intermediate polars has implications for our understanding of magnetic dynamos. In main-sequence stars like the Sun, magnetic fields are thought to be generated by dynamos operating in the convective zones of the star. However, white dwarfs, being compact remnants with little or no convective material, pose a challenge to this paradigm. The intense magnetic fields observed in polars and intermediate polars suggest that alternative dynamo mechanisms may be at play, either during the white dwarf's formation or as a result of its interaction with accreting material. Investigating these mechanisms could provide valuable insights into the origin and evolution of magnetic fields in compact objects. The variability observed in these systems also has broader implications for our understanding of astrophysical variability in general. Many other types of astronomical objects, from neutron stars to active galactic nuclei, exhibit variability on similar timescales. By studying the variability mechanisms in polars and intermediate polars, astronomers can develop models that may be applicable to a wide range of astrophysical systems. For example, the interplay between magnetic fields, accretion flows, and radiation observed in these systems may have analogues in accreting black holes or young stellar objects. Furthermore, polars and intermediate polars are valuable targets for multi-wavelength observations. Their emissions span a broad range of the electromagnetic spectrum, from X-rays and ultraviolet light to optical and infrared wavelengths. Each wavelength provides a different piece of the puzzle, revealing information about the temperature, density, and velocity of the accreting material, as well as the strength and geometry of the magnetic field. Coordinated observations across multiple wavelengths allow astronomers to construct a more complete picture of these systems and test theoretical models more rigorously. One of the most exciting developments in recent years has been the discovery of transitional systems that exhibit characteristics of both polars and intermediate polars. These systems challenge the traditional dichotomy between the two classes and suggest that the boundary between them may be more fluid than previously thought. For example, some systems have been observed to switch between states of high and low accretion rates, with corresponding changes in their magnetic and emission properties. These transitions provide valuable opportunities to study the processes that govern the behavior of magnetic binaries and to test theories about their evolution. The discovery of transitional systems has also raised questions about the role of external factors, such as the environment of the binary system, in shaping their behavior. For instance, variations in the donor star's mass loss rate, the presence of additional companions, or interactions with the interstellar medium could all influence the accretion process and the system's overall evolution. Understanding these external influences is crucial for building a more comprehensive picture of how polars and intermediate polars form and evolve over time. As astronomers continue to discover new systems and refine their observational techniques, the study of polars and intermediate polars is poised to yield even more groundbreaking discoveries. Advanced instruments like the James Webb Space Telescope, JWST, and next-generation X-ray observatories promise to provide unprecedented views of these systems, revealing details that were previously beyond our reach. At the same time, advancements in computational modeling are enabling researchers to simulate the complex interactions between magnetic fields, accretion flows, and radiation with greater precision than ever before. These technological advancements are not just enhancing our understanding of polars and intermediate polars. They are also opening new avenues for exploring the broader astrophysical context in which these systems exist. For example, by studying the population of magnetic binaries in different regions of the galaxy, astronomers can gain insights into the history of star formation, the distribution of magnetic fields, and the processes that drive binary evolution on cosmic timescales. The mysteries of polars and intermediate polars are far from fully understood, but each new discovery brings us closer to unraveling their secrets. These systems remind us of the incredible complexity and diversity of the universe, where even the smallest objects can harbor phenomena that challenge our understanding and ignite our imagination. As we continue to study these enigmatic systems, we not only expand our knowledge of the cosmos but also deepen our appreciation for the intricate and interconnected nature of the universe. The interconnected nature of polars and intermediate polars also ties into the larger question of how binary systems evolve and interact over cosmic timescales. For astronomers, these systems act as microcosms of stellar evolution, offering a front-row seat to processes that would otherwise take millions or even billions of years to unfold. The detailed examination of these systems provides a foundation for understanding more massive or complex binaries, including those involving neutron stars or black holes. One of the most fascinating aspects of polars and intermediate polars is how they seem to defy easy classification. Their magnetic fields, accretion processes, and light emissions are often unique to each system, making it difficult to create a one-size-fits-all model. This uniqueness means that every new discovery forces astronomers to reconsider their theories and adapt their understanding to accommodate the growing diversity of these objects. Take, for example, the phenomenon of asynchronous polars, which blur the lines between polars and intermediate polars. These systems exhibit behavior that is not fully synchronized, but neither do they have the fully developed accretion disks typical of intermediate polars. Instead, they exist in a sort of hybrid state that challenges existing models of magnetic accretion. Studying such systems is crucial because they provide direct evidence of how systems can transition from one state to another, helping astronomers refine their models of binary evolution. Another area of active research involves the long-term magnetic field evolution of these systems. The magnetic fields of white dwarfs and polars and intermediate polars are thought to be remnants of their progenitor stars. But how these fields are maintained or modified over time remains an open question. Some theories suggest that the accretion process itself may amplify or sustain the magnetic field, while others propose that the field gradually decays as the white dwarf ages. Observing a wide variety of systems at different stages of their evolution is key to resolving these questions. The role of magnetic field strength in shaping the accretion process is another area ripe for exploration. In polars, the intense magnetic field funnels material directly onto the poles, creating a starkly different accretion geometry compared to systems with weaker fields. This has a profound impact on the observable properties of the system, including its variability and spectral energy distribution. By comparing systems with different magnetic field strengths, astronomers can better understand how magnetic fields influence accretion in other astrophysical contexts, such as around neutron stars or black holes. Intermediate polars, with their weaker magnetic fields, provide a natural laboratory for studying the transition between magnetically channeled and disk-dominated accretion. These systems often exhibit a mixture of behaviors, with some material following magnetic field lines while the rest forms a truncated accretion disk. This hybrid nature makes them invaluable for testing theories of magnetohydrodynamics, MHD, which describe the behavior of electrically conducting fluids in the presence of magnetic fields. MHD simulations of intermediate polars have already provided insights into how accretion flows behave under different conditions, but much work remains to be done. One particularly intriguing question is how the magnetic fields in these systems interact with the surrounding interstellar environment. In some cases, the magnetic fields of polars and intermediate polars may extend far beyond the immediate vicinity of the binary system, influencing the motion of nearby gas and dust. This could have implications for the formation of new stars and planetary systems in the vicinity, as well as for the distribution of material in the galaxy. The emission properties of polars and intermediate polars also make them excellent candidates for for studying high-energy astrophysical phenomena. The X-rays emitted by these systems, for example, are among the most energetic events observable in the universe. These X-rays originate from the shock-heated material at the accretion hotspots, where temperatures can reach millions of degrees. By analyzing the X-ray spectra of these systems, astronomers can gain insights into the physical conditions near the white dwarf, including the density, temperature, and composition of the accreting material. Moreover, the study of polars and intermediate polars has important implications for our understanding of compact objects in general. White dwarfs, neutron stars, and black holes all represent the final stages of stellar evolution, but they exhibit vastly different properties due to their differing masses and compositions. Polars and intermediate polars provide a unique window into the behavior of white dwarfs, complementing studies of neutron stars and black holes and helping to complete the picture of how stars evolve and die. These systems are also important for understanding the end stages of binary evolution. In many cases, the intense mass transfer occurring in polars and intermediate polars is thought to lead to the eventual merger of the two stars. Such mergers can produce a variety of outcomes, including the formation of a single massive white dwarf, a neutron star, or even a black hole. In some cases, the merger may trigger a Type I supernova, which plays a crucial role in enriching the galaxy with heavy elements and serving as a standard candle for measuring cosmic distances. Another exciting avenue of research involves the use of polars and intermediate polars as natural laboratories for testing fundamental physics. For example, the strong magnetic fields in these systems can produce extreme conditions that are difficult to replicate in terrestrial laboratories. By studying how matter behaves in these environments, scientists can test theories of plasma physics, radiation transport, and even quantum mechanics under extreme conditions. In addition to their scientific importance, polars and intermediate polars also have a certain aesthetic appeal. Their light curves, with their periodic fluctuations and dramatic outbursts, are a testament to the dynamic and ever-changing nature of the universe. For amateur astronomers and professional researchers alike, observing these systems is a reminder of the beauty and complexity of the cosmos. As we look to the future, the study of polars and intermediate polars is poised to benefit from new technologies and observational capabilities. The next generation of telescopes, such as the Vera C. Rubin Observatory and the European Extremely Large Telescope, will provide unprecedented sensitivity and resolution, allowing astronomers to discover and study these systems in greater detail than ever before. Advances in computational power will also enable more sophisticated simulations of these systems, helping to unravel the complex interactions between magnetic fields, accretion flows, and radiation. Polars and intermediate polars are more than just fascinating astrophysical objects. They are key pieces of the puzzle that is the universe. By studying these enigmatic systems, we not only deepen our understanding of the cosmos but also push the boundaries of what is possible in science, technology, and human curiosity. The future of research into polars and intermediate polars is bright, with new discoveries and breakthroughs on the horizon. As observational techniques continue to improve, astronomers are uncovering subtler and more intricate details about these systems, challenging previously held assumptions and opening new avenues for exploration. For example, the advent of high-resolution spectroscopy and time-domain surveys is enabling scientists to map the accretion regions on white dwarfs in unprecedented detail. These observations can reveal the structure and dynamics of the accreting material, shedding light on how it interacts with the strong magnetic fields of the white dwarf. In addition to new observations, theoretical advancements are playing a crucial role in advancing our understanding of these systems. Theoretical models of accretion and magnetic interactions are becoming increasingly sophisticated, incorporating more realistic physics and three-dimensional geometries. These models are essential for interpreting the complex light curves and spectra of polars and intermediate polars, as well as for predicting their long-term evolution. By combining observations and simulations, researchers can test their theories against real data, refining their understanding of the fundamental processes at work. One of the most intriguing aspects of polars and intermediate polars is their potential connection to other astrophysical phenomena. For instance, The strong magnetic fields and intense radiation produced by these systems could influence their surroundings in ways that are not yet fully understood. Some researchers have suggested that the magnetic fields of polars and intermediate polars could interact with the interstellar medium, creating bow shocks or other features that could be detected in radio or infrared wavelengths. These interactions could provide valuable insights into the role of magnetic fields in shaping the galaxy's structure and dynamics. Another area of active research is the search for variations in the magnetic field strength of white dwarfs in polars and intermediate polars. While the magnetic fields of these systems are generally stable over short timescales, there is evidence to suggest that they may evolve over longer periods. Understanding the mechanisms behind this evolution could have important implications for our understanding of magnetic field generation and decay in compact objects. It could also help to explain the diversity of magnetic field strengths observed in these systems, from the relatively weak fields of intermediate polars to the extreme fields of highly magnetized polars. The study of polars and intermediate polars also has implications for understanding the broader population of cataclysmic variables. These systems represent a subset of cataclysmic variables in which magnetic fields play a dominant role, but they are part of a larger family of interacting binary stars. By studying the similarities and differences between polars, intermediate polars, and other types of cataclysmic variables, researchers can gain a more comprehensive understanding of how binary systems evolve and interact. This knowledge can also be applied to other types of binary systems, such as X-ray binaries and symbiotic stars, which share many of the same physical processes. One particularly exciting prospect is the potential for discovering new types of magnetic cataclysmic variables that do not fit neatly into the categories of polars or intermediate polars. The diversity of these systems suggests that there may be other configurations or behaviors that have not yet been observed. For example, there could be systems with unusual magnetic field geometries, accretion patterns, or orbital dynamics that challenge existing models. Identifying and studying such systems could provide valuable insights into the range of possibilities for binary interactions and magnetic accretion. The role of polars and intermediate polars in galactic evolution is another area of interest. These systems are thought to contribute to the population of white dwarfs in the galaxy, as well as to the chemical enrichment of the interstellar medium through nova outbursts. By studying the rates and outcomes of these outbursts, researchers can better understand the contribution of cataclysmic variables to the chemical evolution of the galaxy. This, in turn, has implications for the formation and evolution of stars and planetary systems, as well as for the overall dynamics of the Milky Way. In recent years, there has been growing interest in the potential for polars and intermediate polars to serve as laboratories for testing fundamental physics. The extreme conditions in these systems, including strong magnetic fields, high temperatures, and rapid rotations, provide a unique environment for studying phenomena that cannot be easily replicated on Earth. For example, the intense X-ray emission from these systems can be used to study the properties of highly ionized plasma, while their rapid variability can be used to test theories of time-dependent accretion and magnetic field interactions. Another exciting development is the use of polars and intermediate polars as probes of the interstellar medium. The X-rays emitted by these systems can interact with the interstellar gas and dust along the line of sight, creating absorption and scattering features that can be used to study the properties of the intervening material. By analyzing these features, astronomers can learn about the density, composition, and distribution of gas and dust in the galaxy, as well as about the processes that shape the interstellar medium. The study of polars and intermediate polars is also benefiting from advancements in multi-wavelength astronomy. Observations across the electromagnetic spectrum, from radio to gamma rays, are providing a more complete picture of these systems and their behavior. For example, radio observations can reveal the presence of jets or outflows, while infrared observations can probe the cool material in the accretion stream or the secondary star. By combining data from multiple wavelengths, researchers can gain a deeper understanding of the physical processes at work in these systems and their impact on their surroundings. As we continue to explore the universe, polars and intermediate polars will undoubtedly remain a focal point of research. Their unique combination of magnetic fields, accretion processes, and binary interactions makes them ideal laboratories for studying a wide range of astrophysical phenomena. Whether through detailed observations, advanced simulations, or new discoveries, the study of these systems will continue to push the boundaries of our knowledge and inspire new questions about the universe and our place within it. The mysteries of polars and intermediate polars are far from being fully unraveled. Their complexity lies not only in the intricate dynamics of their magnetic fields and accretion processes, but also in their broader connections to astrophysical phenomena that extend beyond their immediate systems. These enigmatic binary systems challenge our understanding of magnetism, gravity, and the evolution of stars, offering a fascinating window into the forces that shape the universe. One particularly intriguing question is how polars and intermediate polars evolve over time. While significant progress has been made in understanding their current behavior, their origins and ultimate fates remain less certain. It is believed that these systems begin as whiter binaries, where the white dwarf accretes material from a donor star as it evolves off the main sequence. However, the role of magnetic fields in shaping this evolution is not fully understood. For instance, how does the magnetic field of the white dwarf develop or change as the system evolves? Does it remain constant, or does it weaken over time as the white dwarf cools and accretion slows? These questions are critical for constructing accurate models of binary star evolution. Another area of active investigation is the connection between polars, intermediate polars, and other types of compact binary systems. For example, some researchers have suggested that polars and intermediate polars could be evolutionary precursors to certain types of neutron star binaries. As the white dwarf in an intermediate polar accretes material and grows in mass, it could eventually reach the Chandrasekhar limit, collapsing into a neutron star. If this occurs, the system could transition into a high-mass X-ray binary, where the neutron star continues to accrete material from its companion. This scenario highlights the potential for polars and intermediate polars to provide insights into the life cycles of compact objects and the pathways that lead to their formation. The interplay between magnetic fields and accretion flows is another fascinating aspect of polars and intermediate polars that continues to capture the attention of researchers. In many systems, the magnetic field of the white dwarf is strong enough to channel accreting material directly onto its magnetic poles, creating hotspots that emit intense radiation. However, the details of this process are still not fully understood. For example, what determines the precise location and size of the accretion regions? How does the interaction between the magnetic field and the accretion flow influence the variability observed in these systems? These questions are central to understanding the complex dynamics of magnetic accretion and the unique observational characteristics of polars and intermediate polars. Recent observations have also revealed surprising variations in the accretion rates of polars and intermediate polars. Some systems exhibit episodes of enhanced accretion, where the mass transfer rate from the donor star increases significantly. These episodes, known as high states, can last for days, weeks, or even months before the system returns to a lower accretion rate. The causes of these high states are not yet fully understood, but they may be related to changes in the magnetic field, variations in the donor star's mass loss rate, or instabilities in the accretion disk, if present. Understanding these variations is essential for building a complete picture of the accretion processes in these systems. One of the most exciting developments in the study of polars and intermediate polars is the potential for discovering new systems through upcoming astronomical surveys. Projects like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, and space-based missions like Gaia and the upcoming Euclid telescope are expected to uncover thousands of new cataclysmic variables, including polars and intermediate polars. These surveys will provide a wealth of data on their variability, orbital periods, and spatial distribution, enabling researchers to study their properties on a much larger scale than ever before. Additionally, the detection of gravitational waves from compact binary systems has opened a new window for studying polars and intermediate polars. While gravitational wave signals from these systems are expected to be much weaker than those from neutron star or black hole mergers, advanced detectors like LISA, Laser Interferometer Space Antenna, could potentially detect signals from close binary systems with strong gravitational interactions. Such observations would provide unique insights into the orbital dynamics and mass transfer processes in these systems, complementing traditional electromagnetic observations. The role of polars and intermediate polars in understanding broader astrophysical processes cannot be overstated. For instance, their intense X-ray and UV radiation could influence the formation and evolution of planets in nearby systems. The strong magnetic fields of these systems could also play a role in shaping the surrounding interstellar medium, creating cavities or bubbles that affect the distribution of gas and dust in the galaxy. By studying these interactions, researchers can gain a deeper understanding of the complex interplay between compact objects and their environments. In the realm of fundamental physics, polars and intermediate polars serve as natural laboratories for studying extreme magnetic fields, plasma physics, and high-energy radiation. The intense conditions in these systems provide a unique opportunity to test theories of magnetohydrodynamics, radiative transfer, and particle acceleration. For example, the synchrotron and cyclotron radiation emitted by these systems can be used to study the properties of relativistic electrons and magnetic fields in extreme environments. These studies have implications not only for astrophysics but also for understanding similar processes in other contexts, such as laboratory plasma experiments and planetary magnetospheres. The exploration of polars and intermediate polars is a testament to the power of human curiosity and the drive to understand the universe. These systems represent a delicate balance of forces, gravity, magnetism, and angular momentum, all working together to create phenomena that are both beautiful and mysterious. As our observational and theoretical tools continue to advance, we can expect to uncover even more surprising and profound insights into these enigmatic systems. Whether through the discovery of new systems, the development of more sophisticated models, or the integration of data from multiple wavelengths, the study of polars and intermediate polars will continue to be a rich and rewarding field of research. The journey into understanding polars and intermediate polars continues to illuminate not only the specific mechanics of these fascinating binary systems, but also the broader context of astrophysical phenomena. Their importance extends far beyond their unique structure and behavior, contributing to our comprehension of magnetic fields, accretion processes, and the life cycles of stellar objects. One crucial aspect of polars and intermediate polars that remains an active area of research is their contribution to the galactic population of X-ray sources. X-rays emitted by these systems arise primarily from the hot accretion regions near the magnetic poles of the white dwarf. These high-energy emissions make polars and intermediate polars important contributors to the overall X-ray luminosity of our galaxy. Understanding the distribution and characteristics of these systems helps astronomers piece together the broader picture of X-ray binary populations and their role in the galactic ecosystem. Recent advancements in X-ray observatories, such as Chandra and XMM Newton, have provided unprecedented insights into the properties of polars and intermediate polars. High-resolution X-ray spectroscopy has revealed intricate details about the composition and temperature of the accretion flows, as well as the magnetic field strengths of white dwarfs in these systems. By studying the X-ray spectra of multiple systems, researchers have identified distinct patterns and correlations that point to fundamental physical processes governing their behavior. One of the most intriguing questions in this field is the role of magnetic field alignment in shaping the accretion process. In polars, the magnetic field of the white dwarf is strong enough to completely suppress the formation of an accretion disk, causing material to flow directly onto the magnetic poles. In intermediate polars, the magnetic field is weaker, allowing for a partial accretion disk to form before being truncated by the magnetic field. The precise mechanisms governing this transition remain poorly understood. What determines the strength of a white dwarf's magnetic field? How does the alignment of the magnetic field with the binary orbit influence the accretion flow? These questions are critical for building a unified model of magnetic accretion across different types of compact binary systems. Another fascinating area of study is the impact of polars and intermediate polars on their donor stars. The intense radiation and magnetic fields generated by the white dwarf can have profound effects on the companion star. For instance, the high-energy emissions from the accretion regions can heat the inner face of the donor star, creating a phenomenon known as irradiation. This heating can influence the structure and mass loss rate of the donor star, potentially altering the evolution of the binary system. In some cases, the magnetic field of the white dwarf can also induce star spots or other magnetic activity on the donor star, further complicating the dynamics of the system. The variability observed in polars and intermediate polars provides another rich avenue for investigation. Many of these systems exhibit periodic variations in brightness, corresponding to the orbital period of the binary or the spin period of the white dwarf. However, some systems also show irregular or quasi-periodic variations, which are thought to arise from instabilities in the accretion flow. For example, changes in the magnetic field configuration or fluctuations in the mass transfer rate can lead to complex and unpredictable variations in the system's light curve. Understanding these variability patterns requires detailed theoretical models and extensive observational data, often spanning multiple wavelengths. The detection of polar and intermediate polar candidates in other galaxies represents an exciting frontier for this field. While most known systems are located within the Milky Way, advances in telescope technology have made it possible to identify similar systems in nearby galaxies, such as the Magellanic Clouds and Andromeda. Observing these systems in different galactic environments can provide valuable insights into how metallicity, star formation history, and other factors influence the formation and evolution of magnetic cataclysmic variables. Polars and intermediate polars also serve as natural laboratories for studying extreme magnetic fields, which are among the strongest known in the universe. The cyclotron and synchrotron radiation emitted by these systems provide a unique opportunity to study the properties of magnetic fields and relativistic particles under conditions that cannot be replicated on Earth. These studies have implications for understanding other astrophysical phenomena, such as magnetars, pulsars, and even black hole accretion disks. As observational capabilities continue to improve, the potential for new discoveries in this field is immense. Upcoming facilities like the Square Kilometre Array, SK, and the European Extremely Large Telescope, ELT, promise to revolutionize our understanding of polars and intermediate polars by providing unparalleled sensitivity and resolution. These instruments will enable researchers to study faint and distant systems, probe their variability on short timescales, and investigate their role in the broader context of binary star populations. The study of polars and intermediate polars is also closely tied to the quest for a deeper understanding of fundamental physics. For example, the extreme conditions in these systems provide a unique testing ground for theories of magnetohydrodynamics, plasma physics, and radiative transfer. By comparing theoretical models with observations, researchers can refine their understanding of these processes and apply their findings to other areas of astrophysics. Moreover, the potential for detecting gravitational waves from compact binary systems opens up new possibilities for studying polars and intermediate polars. While current detectors like LIGO and Virgo are not sensitive enough to detect signals from these systems, future space-based detectors like LISA could potentially observe gravitational wave emissions from close binaries with strong gravitational interactions. Such detections would provide a new and complementary perspective on the dynamics of these systems, offering insights that are inaccessible through electromagnetic observations alone. The mysteries of polars and intermediate polars highlight the intricate interplay between gravity, magnetism, and stellar evolution. These systems challenge our understanding of the universe, offering a glimpse into the extreme conditions that shape the cosmos. As researchers continue to explore these enigmatic binary systems, they are not only uncovering the secrets of individual stars but also shedding light on the fundamental forces that govern the universe. The narrative of polars and intermediate polars extends deeper, connecting their peculiarities to some of the most profound cosmic phenomena. Their existence isn't just a quirk of stellar evolution, it is a gateway to understanding the delicate balances of forces at play in the universe. These systems, with their extreme environments and unique behaviors, serve as cosmic laboratories where the boundaries of astrophysical theories are tested. One of the most compelling aspects of polars is the nature of their accretion processes, entirely governed by the magnetic field of the white dwarf. Unlike standard binary systems where matter flows steadily into a disk before reaching the compact star, the magnetic dominance in polars creates a more direct, chaotic route. This accretion flow forms streams that are funneled directly onto the magnetic poles of the white dwarf, generating intense heat and energy. The resulting emissions, spanning from ultraviolet to X-rays, make these systems some of the most luminous objects in their respective energy bands. However, what truly makes polars stand out is the synchronization of their orbital and spin periods. This synchronicity implies a remarkable interaction between the magnetic field of the white dwarf and the surrounding material. The exact mechanisms that enforce this synchronization remain an area of active study, with theories suggesting magnetic torques or tidal forces as possible culprits. This behavior poses intriguing questions about the long-term evolution of these systems. How do magnetic fields evolve over time in polars? Do they weaken or strengthen as the white dwarf accretes more material? These questions are pivotal to understanding not only polars but also the broader class of magnetic stars. Intermediate polars, by contrast, offer a more complex picture. In these systems, the magnetic field of the white dwarf is not strong enough to synchronize the spin and orbital periods, resulting in a partial accretion disk. This truncated disk creates its own set of challenges for astronomers. The flow of material through the disk before it is captured by the magnetic field introduces a rich tapestry of variability, making intermediate polars excellent targets for time-domain astronomy. Their multi-periodic light curves, which often exhibit both the orbital and spin periods of the system, provide a wealth of information about the dynamics of accretion and the influence of magnetic fields. The distinction between polars and intermediate polars also sheds light on the diversity of magnetic white dwarfs. Observations suggest that the magnetic fields of white dwarfs and polars can reach up to several 100 million Gauss, among the strongest known magnetic fields in stellar objects. Intermediate polars, on the other hand, typically exhibit weaker fields, in the range of a few million to tens of millions of Gauss. This disparity raises fascinating questions about the origins of these magnetic fields. Are they a relic of the white dwarf's progenitor star, or do they develop during the white dwarf's evolution? Understanding the source of these magnetic fields could unravel fundamental aspects of stellar physics. In addition to their accretion dynamics, polars and intermediate polars are also remarkable for their variability. Observational campaigns using optical, ultraviolet, and X-ray telescopes have revealed a plethora of variability timescales in these systems, ranging from seconds to decades. Short-term variability, such as flickering and quasi-periodic oscillations, often arises from instabilities in the accretion flow. These rapid changes provide a unique glimpse into the immediate environment of the white dwarf, revealing how matter interacts with magnetic fields under extreme conditions. Long-term variability, on the other hand, is often linked to changes in the mass transfer rate from the donor star. This rate can fluctuate due to factors such as star spot cycles or changes in the gravitational interaction between the two stars. Some systems even exhibit states of high and low accretion, where the mass transfer rate changes dramatically over years or decades. These transitions offer invaluable opportunities to study how binary systems adapt to changes in their environment and internal dynamics. A particularly intriguing phenomenon observed in some polars is the so-called self-regulation of accretion. In these systems, the intense radiation generated by the accretion process can influence the donor star, modulating the flow of material onto the white dwarf. For instance, the radiation pressure can temporarily reduce the mass transfer rate, leading to periods of lower luminosity. This feedback loop creates a delicate balance between the forces driving and inhibiting accretion, adding yet another layer of complexity to the behavior of these systems. The study of polars and intermediate polars also intersects with other areas of astrophysics, including the search for exoplanets. In some cases, variations in the light curves of these systems have been attributed to the presence of a third body, such as a planet or brown dwarf. These discoveries not only expand our understanding of the diversity of planetary systems, but also provide a unique perspective on how planets can survive and interact within extreme environments. Looking to the future, advancements in observational technology promise to revolutionize our understanding of polars and intermediate polars. Next-generation X-ray observatories, such as Athena, will provide unprecedented sensitivity and resolution, enabling detailed studies of the accretion regions in these systems. Meanwhile, large-scale optical surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will identify new candidates for study, expanding the known population of these enigmatic objects. In addition to observational progress, theoretical modeling is playing a crucial role in unraveling the mysteries of these systems. Sophisticated simulations of magnetized accretion flows are shedding light on the complex interplay between magnetic fields, gravity, and radiation. These models not only enhance our understanding of polars and intermediate polars but also have broader implications for other astrophysical systems, such as neutron stars and black holes. As we continue to explore the universe, polars and intermediate polars remind us of the incredible diversity of cosmic phenomena. These systems challenge our understanding of fundamental physics, offering a glimpse into the extreme conditions that exist in the universe. They are a testament to the power of magnetic fields, the resilience of stars, and the intricate dance of matter and energy that shapes the cosmos. The study of polars and intermediate polars also sparks new questions about the life cycles of stars and their evolution. As binary systems like these evolve, they reveal much about the fate of stars as they age and eventually transition into white dwarfs. When stars like our Sun reach the end of their lives, they shed their outer layers, leaving behind a dense core that eventually becomes a white dwarf. In a binary system, the interaction between the white dwarf and its companion star can continue to evolve, and over time, the dynamics of accretion, magnetic fields, and stellar winds can reshape the system in dramatic ways. This process highlights the importance of these binary systems in the broader picture of stellar evolution. In fact, the dynamics of the accretion flow onto white dwarfs and systems like polars and intermediate polars can help us understand the processes of mass transfer and angular momentum loss, which play a crucial role in shaping the final stages of a star's life. As material from the companion star is pulled toward the white dwarf, it can lose angular momentum due to the gravitational interaction between the two stars. This loss of angular momentum often causes the orbit to decay over time, which can result in the eventual merger of the two stars. These mergers are not just fascinating in terms of the physics involved, they also have profound implications for the evolution of the binary system and may even lead to the creation of other exotic objects, such as double white dwarfs, neutron stars, or black holes. Moreover, the unique interactions in these systems can also reveal insights into the processes that govern other types of compact objects, such as neutron stars and black holes. By studying the behavior of polars and intermediate polars, scientists can gain a better understanding of the accretion processes that occur in these systems, which are very similar to those found in X-ray binaries, where a compact object pulls matter from a companion star. These systems, with their extreme conditions and intense gravitational fields, provide natural laboratories to study some of the most fundamental questions in astrophysics. The role of magnetic fields in these systems is another crucial aspect that warrants attention. Magnetic fields are not just important for regulating the accretion flow, they also govern many of the phenomena we observe in polars and intermediate polars, such as the emission of X-rays, ultraviolet radiation, and optical light. The strength and configuration of the magnetic field can influence how matter accretes onto the white dwarf, as well as the types of radiation emitted. In polars, for instance, the magnetic field is so strong that it completely disrupts the formation of an accretion disk, channeling material directly to the poles of the white dwarf. The resulting radiation is concentrated in beams, which can sweep across our line of sight, causing periodic changes in the observed brightness of the system. In intermediate polars, the magnetic field is weaker, and an accretion disk can form around the white dwarf, but the material within the disk is still influenced by the magnetic field. This results in a more complex and variable emission pattern, with both disk and magnetic components contributing to the system's overall light curve. The study of these emission patterns provides valuable information about the structure and dynamics of the accretion flow, and can even give insights into the geometry of the magnetic field itself. In many ways, polars and intermediate polars serve as natural laboratories for testing our understanding of magnetic accretion processes in extreme environments. The study of these systems also holds promise for discovering new phenomena that could have far-reaching implications for astrophysics. For example, Some researchers believe that studying the variability in polars could shed light on the nature of magnetic activity in white dwarfs, which could eventually help us understand how stars like our Sun will behave in their later stages. In addition, the interplay between accretion and magnetic fields in these systems may provide new insights into the behavior of matter under extreme conditions, including the behavior of matter in the vicinity of black holes or during the mergers of compact objects. These investigations have the potential to open up entirely new areas of research in the field of astrophysics. One particularly exciting avenue of research involves the potential discovery of new types of stars or exotic objects that exist in the same extreme environments as polars and intermediate polars. For example, some scientists are investigating the possibility that the dynamics of these systems could lead to the formation of new types of magnetically powered stars, such as magnetars. Magnetars are a class of neutron stars with incredibly strong magnetic fields, and they are thought to be powered by the same processes that govern polars and intermediate polars. If such stars are found, it could dramatically change our understanding of the relationship between magnetic fields and stellar evolution, and may even offer a glimpse into the final stages of stellar collapse. In addition, the study of polars and intermediate polars is closely tied to the field of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of black holes or neutron stars. The processes that govern accretion in polars and intermediate polars can lead to complex gravitational wave signatures that can be detected by sensitive instruments such as LIGO and Virgo. By studying the gravitational waves from these systems, scientists hope to gain a better understanding of the extreme physics at play in the compact objects that make up these systems, as well as the properties of the gravitational waves themselves. The search for more polars and intermediate polars is also a key part of the larger quest to understand the population of white dwarfs in the universe. White dwarfs are one of the most common types of stellar remnants, and they can be found in a variety of different environments, from isolated objects in the Milky Way to members of binary systems. By identifying more polars and intermediate polars, astronomers can learn more about the different stages in the evolution of these stars and their interactions with companion stars. This, in turn, could help to refine models of stellar evolution, particularly the final stages of a star's life cycle. To aid in the discovery of new polars and intermediate polars, astronomers are increasingly relying on advanced observational techniques, such as large-scale surveys and space-based telescopes. For instance, surveys like the Sloan Digital Sky Survey (SDSS) and the Pan-STARRS survey have already discovered many new white dwarf systems, including several polars and intermediate polars. The upcoming James Webb Space Telescope (JWST) and future X-ray observatories like the Athena mission will further expand our ability to study these systems in unprecedented detail, revealing new insights into the nature of accretion, magnetic fields, and stellar evolution. As technology continues to advance, our understanding of these mysterious systems will continue to deepen. New discoveries will undoubtedly challenge our existing models and open up entirely new areas of research, ultimately helping us to answer some of the most fundamental questions in astrophysics. The strange behavior of polars and intermediate polars may seem puzzling at first, but each new discovery brings us one step closer to understanding the intricate and complex forces that govern the universe. And who knows? Perhaps in the far future, the study of these systems will lead to even greater revelations about the nature of stars, black holes, magnetic fields, and the cosmos itself. The continued exploration of polars and intermediate polars is not just a deep dive into the unknown, but it is also a journey into understanding how extreme environments shape the universe around us. The significance of these systems lies in the unique combination of forces at play, particularly the interaction between the strong magnetic fields of white dwarfs and the accretion of material from companion stars. These processes create an environment so extreme that it challenges our understanding of matter, energy, and even the very fabric of spacetime. In fact, the study of polars and intermediate polars goes beyond simply understanding these systems on their own. Their behavior may also provide valuable insights into other cosmic phenomena that occur in more distant or more extreme environments. For example, the high-energy radiation emitted by these systems, particularly in the X-ray and ultraviolet wavelengths, offers a window into the most energetic processes in the universe. This radiation can help us study the behavior of matter in extremely hot and dense environments, shedding light on the interactions of particles under conditions that we can't replicate on Earth. One area where this research is particularly relevant is in the study of supernovae, which are the explosive deaths of massive stars. Supernovae are one of the most energetic events in the universe and are thought to be responsible for the creation of heavy elements, as well as the dispersal of those elements into the surrounding space. Polars and intermediate polars can serve as analogues for some of the processes that occur in the aftermath of a supernova, such as the accretion of material onto compact objects and the influence of magnetic fields on the flow of matter. Understanding these processes can help astronomers better interpret the behavior of supernovae and the evolution of the stars that produce them. Furthermore, the study of polars and intermediate polars can provide clues to the origin of certain types of cosmic explosions, such as gamma-ray bursts, GRBs. These bursts are among the most powerful events observed in the universe, and their origins are still the subject of intense research. One hypothesis is that they are caused by the collapse of massive stars into black holes or neutron stars. By studying the accretion processes in binary systems like polars and intermediate polars, scientists can gain a deeper understanding of the types of interactions that could trigger such explosive events, providing crucial information about the conditions needed for the formation of black holes and the production of gamma-ray bursts. Additionally, the study of these binary systems has implications for our understanding of the formation of stellar binaries and the dynamics of stellar populations. Many of the most intriguing objects in the universe, such as neutron stars, black holes, and magnetars, are believed to form in binary systems, where one star interacts closely with another. Polars and intermediate polars are among the best examples of such systems, offering a unique opportunity to study the complex interactions between stars in close proximity. By learning more about the behavior of these systems, astronomers can develop better models for the formation and evolution of binary systems, improving our understanding of how such systems evolve over time. As we uncover more about the strange and mysterious behavior of polars and intermediate polars, we also begin to appreciate the broader context of our place in the universe. These systems are reminders that the cosmos is a far more complex and dynamic place than we can ever fully understand. Every new discovery adds another layer to the intricate tapestry of the universe, revealing new insights into the forces that govern the cosmos. Whether it's the unexpected behavior of white dwarfs, the enigmatic effects of magnetic fields, or the complex interactions between stars and binary systems, the study of polars and intermediate polars continues to push the boundaries of our knowledge and challenge our understanding of the universe. What is truly remarkable about these systems is how much they reveal about the unseen aspects of the universe. Magnetic fields, which are invisible to the naked eye, play a crucial role in shaping the dynamics of polars and intermediate polars, just as they do in many other cosmic phenomena. Their effects, though often subtle, can dramatically alter the way matter behaves and the way radiation is emitted from these systems. As we learn more about these invisible forces, we gain a deeper appreciation for the complexity of the universe and the ways in which unseen forces govern the behavior of everything from the smallest particles to the largest cosmic structures. The search for more polars and intermediate polars will undoubtedly continue to be a major focus for astronomers in the coming years. With advanced observational tools and new technologies, the possibilities for discovering new systems and understanding their behavior are expanding rapidly. The upcoming generation of space-based telescopes, such as the James Webb Space Telescope, will open up new windows into the extreme environments of polars and intermediate polars, allowing us to study these systems in greater detail than ever before. Additionally, the continued development of gravitational wave observatories, like LIGO and Virgo, will enable us to probe the dynamics of these systems in a completely new way, providing insights that could transform our understanding of compact objects, accretion, and magnetic fields. Looking ahead, the role of polars and intermediate polars in the broader context of astrophysics cannot be overstated. They serve as a bridge between the known and the unknown, offering clues to the workings of the most mysterious and extreme regions of the universe. As we continue to study these systems, we will undoubtedly uncover even more surprising discoveries that challenge our understanding of the universe and push the limits of what we thought was possible. Moreover, the study of these systems might eventually have practical implications for other areas of science and technology. The phenomena observed in polars and intermediate polars, such as the behavior of material under intense magnetic fields and high-energy radiation, could inspire new advancements in fields ranging from materials science to energy generation. For example, understanding the behavior of plasma and the extreme environments of these systems could lead to advances in fusion energy research, which seeks to replicate the processes that power stars. In this way, the exploration of polars and intermediate polars could contribute not only to our understanding of the cosmos but also to the development of new technologies that could shape the future of life on Earth. The strange behavior of polars and intermediate polars is not just a curiosity, it is a reflection of the hidden wonders that the universe has to offer. The more we study these systems, the more we realize how much we have yet to learn about the forces that shape the cosmos. The mysteries of these systems are only beginning to be unraveled, and as we continue to push the boundaries of our knowledge, we are sure to make even more exciting discoveries that will illuminate the path forward in our quest to understand the universe. As we dive deeper into the mechanics of these fascinating binary systems, it's crucial to understand the dynamics between the white dwarf and its companion star in greater detail. The interaction between the two stars within a polar or intermediate polar system creates an environment that is unlike anything we experience on Earth. White dwarfs are the remnants of stars that have exhausted their nuclear fuel and collapsed under gravity, resulting in an incredibly dense object. Despite their small size, these stars have mass comparable to that of the Sun, packed into a volume similar to that of Earth. This intense density gives rise to extraordinarily strong gravitational and magnetic fields. In polar systems, the white dwarf is typically paired with a companion star, often a red dwarf or another low-mass star, which is orbiting the white dwarf at close range. The intense gravitational pull of the white dwarf causes the companion star to shed material. This material forms an accretion disk around the white dwarf, but the strong magnetic field of the white dwarf prevents the material from falling uniformly. Instead, the material is funneled along the magnetic field lines toward the magnetic poles of the white dwarf. This process creates the characteristic behavior of polars, with material accreting onto the white dwarf in concentrated regions near its poles. The resulting interactions between the magnetic fields and the accretion flow generate high-energy X-rays and ultraviolet radiation, which can be detected by telescopes and provide important information about the system. One of the most intriguing aspects of polar systems is the way in which the magnetic field influences the behavior of the accreting material. In the case of a normal accretion disk, material flows inwards towards the compact object due to the effects of gravity. However, in polars, the magnetic field of the white dwarf disrupts this process, channeling the material along the magnetic poles rather than allowing it to fall smoothly into the star. This leads to the formation of an accretion column, where material falls from the inner part of the accretion disk along the magnetic field lines. As the material accelerates toward the poles, it gains immense kinetic energy, which is converted into X-ray radiation as it crashes into the surface of the white dwarf. Intermediate polars, while similar to polars in many ways, are characterized by slightly weaker magnetic fields. In these systems, the accretion disk still forms around the white dwarf, but the magnetic field is not strong enough to completely disrupt the flow of material. Instead, the magnetic field interacts with the inner part of the accretion disk, creating a situation in which the material falls into the white dwarf in a more sporadic manner, rather than in the concentrated beam seen in polars. The result is a system that exhibits a more complex behavior, with varying levels of X-ray emission and changes in the accretion flow over time. This variability in intermediate polars is one of the key differences between them and polars, and it makes intermediate polars particularly interesting to astronomers. The irregular nature of the accretion process in intermediate polars means that they often exhibit flaring behavior, where bursts of X-ray radiation are emitted as the material falls onto the white dwarf. These flares can provide valuable insights into the physics of accretion, magnetic fields, and the behavior of matter in extreme environments. The study of intermediate polars is helping scientists to better understand the complex interplay between magnetic fields and accretion in binary systems. The magnetic fields in both polars and intermediate polars are not static. They evolve over time and can be influenced by the accretion process itself. In some systems, the magnetic field strength of the white dwarf can change as the material from the companion star accretes onto the white dwarf. This can lead to fluctuations in the behavior of the system, including changes in the X-ray emission, the strength of the magnetic field, and even the orientation of the magnetic poles. These fluctuations add another layer of complexity to the study of polars and intermediate polars, and they raise important questions about the long-term evolution of these systems. The behavior of polars and intermediate polars is also closely tied to the concept of spin. White dwarfs in these systems are often observed to rotate at high speeds. The magnetic field of the white dwarf is typically aligned with its spin axis, meaning that as the star rotates, the magnetic poles move in and out of alignment with the accreting material. This leads to a periodic variation in the amount of material being funneled onto the magnetic poles, and thus the amount of radiation being emitted from the system. This periodicity is one of the defining features of many polar systems, and it provides a valuable tool for astronomers studying the dynamics of these systems. In intermediate polars, the spin of the white dwarf is also an important factor. The weaker magnetic field in these systems allows for a more complex interaction between the accretion disk and the white dwarf, resulting in a variety of different spin behaviors. Some intermediate polars exhibit a strong correlation between the rotation of the white dwarf and the X-ray emission, while others display more chaotic behavior. The variability in the spin and accretion rates of these systems is an area of active research, as scientists seek to understand the underlying mechanisms that drive these changes. In addition to their behavior in X-rays, polars and intermediate polars can also be observed in other wavelengths of light, including optical and infrared. The presence of an accretion disk around the white dwarf can cause the system to glow brightly in the optical part of the spectrum, and this emission can be modulated by the accretion process. In some cases, the companion star can also contribute to the optical light from the system, particularly if it is a relatively bright star, such as a red dwarf. The study of these systems in optical and infrared wavelengths provides another piece of the puzzle, helping scientists to piece together a more complete picture of the accretion process and the behavior of the magnetic fields. The study of polars and intermediate polars is also relevant to the broader field of astrophysics because of the insights they provide into the behavior of compact objects, such as white dwarfs, neutron stars, and black holes. These objects are some of the most extreme and mysterious in the universe, and studying the ways in which they interact with their environments is crucial for understanding their properties and their evolution. Polars and intermediate polars are particularly valuable for this purpose because they represent systems where the behavior of the compact object is influenced by both the accretion process and the strong magnetic fields, offering a unique opportunity to study the interplay between these factors. In the coming years, new observatories and technologies will allow for even more detailed observations of polars and intermediate polars. For example, the upcoming launch of the James Webb Space Telescope will enable astronomers to observe these systems in unprecedented detail, particularly in the infrared and optical wavelengths. The next generation of X-ray telescopes, such as the Athena mission, will provide even more sensitive measurements of the X-ray emission from these systems, allowing for more precise measurements of their behavior. These advancements will likely lead to new discoveries about the nature of these fascinating systems, as well as new insights into the physics of compact objects and accretion. As we continue to study polars and intermediate polars, we are not just learning more about the specific systems themselves, but also about the broader processes that govern the universe. The interactions between white dwarfs, their companion stars, and the magnetic fields that shape them provide a unique laboratory for studying some of the most extreme phenomena in astrophysics. The insights gained from this research will help to refine our understanding of binary star systems, accretion processes, and the behavior of compact objects, contributing to a more complete understanding of the universe as a whole. The strange behavior of polars and intermediate polars is just one example of the many mysteries that continue to captivate astronomers and astrophysicists. These systems serve as a reminder of the vast complexity and richness of the cosmos, and they inspire a sense of wonder and curiosity that drives the pursuit of knowledge. As we continue to explore the depths of the universe, we can be sure that the study of these systems will continue to yield new and exciting discoveries, opening up new avenues of research and expanding our understanding of the forces that shape the cosmos. The study of polars and intermediate polars offers much more than just insight into the mechanics of these systems. It also illuminates broader astrophysical principles that apply across various domains of the cosmos. One of the most compelling aspects of these systems is the way in which they challenge our understanding of the behavior of matter and energy under extreme conditions. The magnetic fields in these systems are so powerful that they significantly alter the fundamental properties of the matter that falls onto the white dwarf. This process forces material to behave in ways that are not typically observed in less extreme environments, offering a glimpse into the strange and unknown interactions that take place in the depths of space. As we dive deeper into the study of these unusual systems, we begin to realize that polars and intermediate polars can teach us more about the broader nature of accretion processes. Accretion, the process by which material falls into a gravitational well, is one of the most fundamental phenomena in astrophysics. Whether it's the formation of stars, the growth of black holes, or the evolution of galaxies, accretion is involved in virtually every aspect of cosmic evolution. Polars and intermediate polars provide an excellent laboratory for studying accretion in extreme conditions, where magnetic fields play a crucial role in shaping the flow of material. This role of magnetic fields in the accretion process is particularly important when it comes to understanding how matter behaves in the presence of strong magnetic forces. In typical accretion disks, matter falls inward due to gravitational attraction. However, in polar systems, the magnetic field of the white dwarf twists and distorts the path of the material, causing it to spiral inward along magnetic field lines. This alters the standard model of accretion and provides valuable insight into how magnetic fields can influence the movement of matter in a system. The study of this process helps to refine our understanding of the role of magnetic fields in astrophysical environments, which is essential for understanding everything from the behavior of stars to the dynamics of black holes. Another key insight gained from the study of polars and intermediate polars is the interaction between the compact objects and their surrounding environments. White dwarfs, while seemingly small in comparison to stars like the Sun, are incredibly dense objects that generate intense gravitational and magnetic forces. The material from the companion star is funneled toward the white dwarf, where it heats up and emits a wide range of radiation, from X-rays to optical light. The energy released from these interactions provides a valuable probe into the behavior of matter under extreme conditions and helps scientists to test theoretical models of how compact objects interact with their environments. The observation of flaring events in intermediate polars, in particular, highlights the variability of these systems and the complex dynamics that drive their behavior. Unlike in polar systems, where the accretion process tends to be more stable and predictable, intermediate polars are known for their erratic behavior, with periods of intense X-ray emission followed by quieter phases. These fluctuations in radiation output are closely tied to the irregular flow of material in the accretion disk and the sporadic accretion events that take place. Studying these flare events can provide valuable information about the internal structure of the accretion disk, as well as the processes that govern the flow of material in systems with weaker magnetic fields. In addition to flaring, intermediate polars often exhibit other phenomena that are unique to their type. One such phenomenon is the so-called spin-up of the white dwarf. In many intermediate polars, the white dwarf gradually increases its rotation speed over time, a process that occurs as a result of the accretion of material from the companion star. As material falls onto the surface of the white dwarf, it transfers angular momentum, which causes the star to spin faster. This spin-up effect is not unique to intermediate polars but is more pronounced in these systems due to the weaker magnetic fields and the irregularity of the accretion process. The study of spin-up in intermediate polars is a fascinating area of research, as it provides insight into the long-term evolution of these systems and the ways in which compact objects can interact with their environments over time. The spin behavior of polars and intermediate polars is not just a curiosity. It also has important implications for the study of white dwarfs and other compact objects. The relationship between spin and magnetic field strength is an area of active research, and the unique characteristics of these binary systems provide a natural testing ground for theories about how compact objects behave in binary star systems. By studying the way in which the white dwarf spins and interacts with its companion star, astronomers can learn more about the physics of compact objects, including their internal structures, magnetic field configurations, and the way in which they evolve over time. The behavior of polars and intermediate polars also holds potential for advancing our understanding of the broader dynamics of binary star systems. The gravitational interaction between the white dwarf and its companion star plays a crucial role in shaping the system's overall evolution. As the stars orbit each other, the material from the companion star is funneled toward the white dwarf, resulting in a constant flow of mass. This interaction affects the orbital dynamics of the system, as well as the rate at which material is accreted onto the white dwarf. Understanding the long-term behavior of these systems is important for refining our models of binary star evolution and understanding how different types of stars interact over time. Moreover, these systems can serve as a testbed for our understanding of the general principles of accretion physics. The accretion process is one of the most important processes in astrophysics, influencing everything from the growth of stars to the formation of supermassive black holes at the centers of galaxies. Studying the way in which matter behaves in the extreme conditions found in polars and intermediate polars can help astronomers to develop a more detailed understanding of accretion in other astrophysical systems. By examining the specific processes that take place in these unique binary systems, scientists can gain valuable insights into the broader mechanisms that govern the behavior of matter and energy in the universe. The study of these systems also provides an opportunity to better understand the evolution of stars and white dwarfs. The interactions between the stars and binary systems play a crucial role in determining the fate of each star. In some cases, the material that is accreted onto the white dwarf can cause the star to reach critical mass, leading to a catastrophic explosion known as a Type I supernova. By studying the behavior of polars and intermediate polars, astronomers can learn more about the processes that govern the fate of these stars and gain a deeper understanding of the complex life cycle of stars and binary systems. While much progress has been made in our understanding of polars and intermediate polars, there is still much to learn. The intricate dynamics of these systems, combined with the challenges of observing such distant and extreme objects, make them a particularly difficult subject of study. However, advances in observational technology are helping to shed new light on these fascinating systems. The development of more powerful telescopes and better instruments for observing X-rays, optical light, and other wavelengths of radiation is allowing scientists to explore these systems in greater detail than ever before. In the future, space observatories like the James Webb Space Telescope and upcoming X-ray missions such as the Athena mission will provide new opportunities for studying polars and intermediate polars. These advanced telescopes will enable astronomers to observe these systems in unprecedented detail, revealing new insights into the behavior of white dwarfs, accretion disks, and magnetic fields. The continued exploration of these systems will undoubtedly lead to further discoveries, opening up new avenues of research in the field of astrophysics and deepening our understanding of the most extreme environments in the universe. As we look to the future of space exploration and research, it's clear that the study of polars and intermediate polars will remain an important area of focus. The strange behavior of these systems, coupled with the insights they offer into fundamental astrophysical processes, makes them a key area of research for astronomers and physicists alike. As we continue to unravel the mysteries of these intriguing systems, we not only learn more about the specific systems themselves but also about the broader principles that govern the universe. The study of polars and intermediate polars is an ongoing journey into the heart of the cosmos, and the discoveries we make along the way will continue to shape our understanding of the universe for generations to come. The strange behavior exhibited by polars and intermediate polars is not just a curiosity, but it also opens the door to understanding the larger dynamics of astrophysics. These systems, with their strong magnetic fields and unusual accretion processes, are one of the best examples of how extreme conditions in space can push the limits of our current understanding of stellar behavior. As astronomers and astrophysicists continue to examine these systems, new revelations about magnetism, matter, and accretion are emerging, shifting the focus of research to explore how these phenomena could exist beyond the realms of the binary systems that we currently observe. An important aspect of these systems that is worth emphasizing is the variability in their behavior. Polars and intermediate polars, unlike more stable star systems, do not follow the simple, predictable patterns of behavior that one might expect from traditional stellar systems. This is largely due to the complexity of their accretion mechanisms. In a polar system, for example, the interaction between the magnetic field of the white dwarf and the companion star creates an environment where material is funneled toward the magnetic poles of the white dwarf. This leads to intense, localized regions of high-energy emission and flaring, causing significant fluctuations in the observed radiation. These erratic behaviors provide rich insights into the interplay between gravity, magnetism, and accretion in stellar environments. The variability of intermediate polars is similarly fascinating, with irregularities in the intensity and frequency of radiation emitted. The fact that these systems are characterized by both accretion and magnetic field interactions suggests that they could be a natural laboratory for exploring how matter behaves under diverse influences. One of the core areas of research in these systems is the process of accretion itself, which involves matter being drawn toward a compact object. As this material spirals inward, it heats up and releases energy, contributing to the radiative output that we can observe from Earth. In polar and intermediate polar systems, this process is more complicated due to the intense magnetic fields that distort the accretion flow. The strong magnetic fields of the white dwarfs in these systems lead to the confinement of the accreting material along magnetic field lines, rather than forming a traditional accretion disk. This makes the system behave in a way that is unlike typical accretion phenomena. These magnetic field lines essentially funnel matter onto the poles of the white dwarf, where the material impacts the star's surface, creating high-energy X-ray emissions. These emissions are often intense and variable, and the understanding of how these fields control the flow of material in the system is still being investigated. The interaction between the magnetic fields and the surrounding material also creates a unique and complex radiation spectrum. In polar systems, the material that is funneled toward the white dwarf produces strong X-ray emissions, which can be observed with space-based telescopes. The high-energy radiation is indicative of the high temperatures reached by the accreting material as it impacts the white dwarf's surface. These extreme conditions can cause the material to emit radiation at various wavelengths, from the ultraviolet to the X-ray, and can even lead to flaring events, further complicating our ability to predict and model the behavior of these systems. Intermediate polars present an even more fascinating case because, in these systems, the magnetic field strength is weaker than in polars, which allows the accretion to proceed in a more irregular manner. The material from the companion star does not flow along magnetic field lines as neatly as it does in polar systems, and instead, it tends to form a distorted, asymmetrical disk around the white dwarf. This leads to variations in the emission of radiation, and over time, the system can display sudden bursts of energy, or, conversely, quiet phases with much less observable radiation. Furthermore, intermediate polars also display behavior that is similar to what is observed in other accretion-powered systems, such as X-ray binaries. These systems, which consist of a compact object like a neutron star or black hole, are famous for their periodic bursts of radiation. The difference between intermediate polars and other X-ray binaries lies in the nature of the compact object and the magnetic interaction with the accretion disk. The weaker magnetic fields in intermediate polars do not disrupt the flow of material as dramatically as they do in polars, but they still have a profound impact on the overall dynamics of the system. These magnetic interactions also lead to the phenomenon of spin-up, in which the white dwarf gradually increases its rotation speed as it accretes material. This effect is due to the transfer of angular momentum from the infalling material to the white dwarf, which is a direct consequence of the accretion process. The study of intermediate polars also has far-reaching implications for our understanding of the broader population of compact objects in the universe. By studying the various mechanisms that govern the behavior of these systems, we gain a deeper understanding of how accreting compact objects, whether white dwarfs, neutron stars, or black holes, affect their surrounding environments. Understanding these systems is critical for gaining insight into the processes of star formation, evolution, and the fate of stellar remnants. By investigating how material is accreted onto compact objects, astronomers can better predict the life cycle of stars and binary systems, and the eventual fate of these objects after they have exhausted their nuclear fuel. One of the key challenges in studying polars and intermediate polars is the difficulty in observing these systems with conventional telescopes. The high-energy radiation emitted from these systems is typically in the X-ray and ultraviolet ranges, which are difficult to observe from Earth due to the absorption of these wavelengths by the Earth's atmosphere. This necessitates the use of space-based telescopes, such as NASA's Chandra X-ray Observatory or the European Space Agency's XMM Newton, which are capable of detecting high-energy emissions from these systems. These telescopes have allowed scientists to gather detailed information about the radiation profiles of polars and intermediate polars, shedding light on the complex interactions between the white dwarf and its companion star. In addition to space-based observatories, the growing field of gravitational wave astronomy also has the potential to provide new insights into the behavior of binary systems like polars and intermediate polars. While gravitational waves are typically associated with more extreme events, such as the merging of black holes or neutron stars, the movement and interactions within a binary system can also produce detectable gravitational waves. As detection methods for gravitational waves improve, it is possible that we could learn even more about the dynamics of compact binary systems and how their accretion processes evolve over time. The strange and unpredictable behavior of polars and intermediate polars remains one of the most exciting frontiers in modern astrophysics. These systems, with their magnetic fields, accretion processes, and complex radiation patterns, continue to challenge scientists to refine existing models and develop new theories to explain the phenomena they exhibit. As our observational tools improve, and as we continue to push the boundaries of our knowledge, we can only imagine the further discoveries that await in this strange and distant corner of the universe. Ultimately, the study of polars and intermediate polars is more than just an academic pursuit. These systems represent an opportunity to unlock the mysteries of the universe and understand the fundamental forces that govern the behavior of matter and energy in the most extreme environments. The strange and unpredictable behavior of these systems is not just a curiosity. It is a testament to the complexity and beauty of the universe itself. As new observations continue to push the boundaries of our understanding, the mysteries of polars and intermediate polars will no doubt lead to further breakthroughs in astrophysics. By continuing to study these unique systems, we can begin to unravel the deepest mysteries of how stars, magnetic fields, and accretion processes shape the cosmos, and gain new insights into the origins and evolution of the universe itself. The exploration of these systems will continue to captivate the minds of astronomers and researchers for years to come, providing new knowledge that will challenge, expand, and enrich our understanding of the cosmos. As we continue to investigate polars and intermediate polars, one of the key aspects that captivates researchers is the magnetic field dynamics within these systems. The white dwarfs at the core of these binaries are extraordinary objects in themselves. These stars, which are the remnants of once massive stars, are incredibly dense, and their magnetic fields are some of the strongest in the universe, often millions to billions of times stronger than Earth's magnetic field. These intense magnetic fields not only influence the accretion processes but also have profound effects on the surrounding material, shaping how the system behaves over time. The magnetic fields of white dwarfs are thought to be the result of their initial formation and the processes occurring during their evolution. As the progenitor star exhausts its nuclear fuel and collapses into a white dwarf, the magnetic field generated by the star's earlier convection processes becomes frozen in place, leading to the creation of these powerful fields. In some cases, the magnetic field strength in a white dwarf can be so intense that it significantly alters the motion of the accreting material, causing it to become funneled toward the poles, as previously discussed. This creates what we call polar systems, where the white dwarf's magnetic field directs the infalling matter along the magnetic lines toward the poles, resulting in intense radiation bursts. The study of how these magnetic fields influence the accretion flow is crucial for a deeper understanding of the physics involved. Magnetic fields can exert a force on ionized particles, which, in the case of a binary system, causes the material from the companion star to behave in ways that we would not normally expect in other accreting systems. This causes the accretion process to become highly asymmetric, with the material being drawn into the magnetic poles of the white dwarf instead of forming a smooth, evenly distributed accretion disk. In intermediate polars, the magnetic field is weaker than in pure polars, and the interaction between the accreting material and the magnetic field is less disruptive. This allows for a more conventional accretion disk to form around the white dwarf, but with unique, irregular behavior due to the residual magnetic influence. Moreover, one of the most striking aspects of polars and intermediate polars is their ability to exhibit periodic variations in their emission, which is another manifestation of the complex interaction between the white dwarf and its companion star. In some systems, these variations are linked to the rotation of the white dwarf itself. As the white dwarf rotates, it induces a periodic modulation in the accretion process, causing the radiation from the system to change in intensity over time. This variability can be observed as periodic bursts of X-rays, which are often used by astronomers to study the rotational period of the white dwarf. This is another key area of research that has proven to be both fascinating and challenging, as understanding the precise cause of these fluctuations can offer valuable insights into the dynamics of the entire system. What is particularly interesting is how these periodic changes in brightness can sometimes mimic the behavior of other types of variable stars, such as cataclysmic variables or even certain types of supernovae. This can create a confusion among astronomers, especially when trying to categorize and classify these objects. Polars and intermediate polars may look similar to other variable stars in some respects, but the underlying physics at play in these systems is vastly different. It is these differences that make studying them so important, as they offer unique insights into the behavior of compact objects and the physical processes that govern stellar evolution. The magnetic environment in which the white dwarf operates also creates conditions conducive to the formation of radiation flares. These flares are essentially sudden, intense bursts of energy that are emitted as a result of the energetic interactions between the accreting material and the magnetic field. These flares can be seen across multiple wavelengths, from X-rays to ultraviolet, and they are thought to be caused by the sudden release of magnetic energy within the system. This release of energy is a direct consequence of the magnetic field's influence on the accretion process, causing material to accumulate in localized areas and then suddenly release large amounts of energy in the form of radiation. Flares like this can occur on timescales ranging from minutes to hours, adding another layer of complexity to the already chaotic behavior of these systems. In addition to the fascinating physics at play in polars and intermediate polars, these systems also hold significant value for understanding the broader universe. These unique binary systems offer a rare glimpse into how magnetic fields can shape the behavior of stars and influence their interactions with companion stars. The study of these systems can also shed light on the role of magnetic fields in other astrophysical phenomena, such as stellar winds, coronal mass ejections, and the behavior of supernovae. By studying these systems, we can learn more about the fundamental forces that govern the dynamics of stars and how these forces can vary across different types of stellar systems. Polars and intermediate polars may seem like a niche area of study, but they are, in fact, a critical part of our understanding of the universe. The strange behavior of these systems, with their erratic radiation patterns and complex accretion processes, is a reminder of how much we still have to learn about the forces that shape the cosmos. As technology advances and new observational tools become available, we are likely to gain even more insight into the behavior of these fascinating systems, offering further revelations about the nature of compact objects, magnetic fields, and accretion processes. Perhaps one of the most exciting aspects of studying polars and intermediate polars is their potential to teach us more about the future evolution of binary systems. As these systems evolve, they may eventually reach a point where the interaction between the white dwarf and its companion star leads to the complete accretion of the latter, or the white dwarf may gain enough mass to eventually become a neutron star or even collapse into a black hole. The study of these systems is thus not just a look into the present, but a window into the future of stellar evolution. Moreover, as researchers continue to study these systems in greater detail, they may uncover new phenomena that were previously thought to be impossible. For example, there are indications that some polars and intermediate polars could potentially harbor exotic forms of matter, such as strange matter, which could further deepen our understanding of the nature of matter under extreme conditions. These discoveries could have profound implications for our understanding of physics, challenging existing models and theories and opening the door to new avenues of research. Another exciting possibility lies in the way polars and intermediate polars may help answer fundamental questions about the origin of magnetic fields in the universe. The strength and behavior of the magnetic fields in these systems could provide clues about the formation of magnetic fields in other celestial bodies, including planets and stars. If scientists can pinpoint the exact mechanisms that lead to the formation of such intense magnetic fields, it could have wide-ranging implications for astrophysics, potentially helping to explain the origins of magnetism in various parts of the universe. The study of these magnetic phenomena could even lead to breakthroughs in other scientific fields, such as plasma physics, magnetohydrodynamics, and high-energy astrophysics. Understanding the behavior of plasma in the presence of magnetic fields is crucial for a wide range of applications, including understanding the behavior of fusion reactors, the dynamics of space weather, and the behavior of cosmic plasma in high-energy environments. As the study of polars and intermediate polars progresses, it will likely lead to more than just answers about these specific systems. The insights gained from these binary systems will continue to influence and inspire research in many other areas of astrophysics, making them a key piece of the puzzle in our broader understanding of the universe. With every new discovery, we edge closer to unraveling the mysteries of these extraordinary systems. Polars and intermediate polars are more than just a curiosity. They represent a deep well of knowledge that could one day help us answer some of the most profound questions in astrophysics. The strange, unpredictable behavior of these systems is a reminder that even in the most extreme corners of the universe, there is still so much more to learn and explore. As we continue to explore the mysteries of polars and intermediate polars, it's important to consider how these systems can also offer insights into the broader phenomena of accretion disks, magnetic fields, and stellar evolution. While these systems are often defined by the unique interaction between the magnetic fields of the white dwarf and the material from its companion star, they also share common characteristics with other accreting systems found in the universe. These similarities give researchers a powerful tool to study the behavior of matter in extreme environments, such as the behavior of material as it spirals inward toward a compact object. Accretion disks are common to a wide range of astrophysical systems, from black holes to neutron stars to young stellar objects. However, in polars and intermediate polars, the magnetic field of the white dwarf plays a dominant role in shaping the accretion process. Unlike the smooth, rotating accretion disks observed in non-magnetic systems, these systems exhibit highly irregular, chaotic behavior due to the magnetic field's influence. The presence of a strong magnetic field alters the path of the accreting material, causing it to move in spiral-like patterns that are tightly constrained by the magnetic lines of force. This results in a phenomenon known as magnetic accretion, which is vastly different from the more common disk accretion observed in other systems. The irregularities in the accretion process lead to periodic changes in the brightness of the system, which we have already touched upon. However, it's important to delve deeper into the implications of these brightness variations. The variations in light intensity are not random, but rather exhibit a highly predictable pattern based on the rotational period of the white dwarf. These variations occur because the magnetic field funnels the material onto the poles of the white dwarf, which causes sudden, intense bursts of radiation as the material collides with the star's surface. The periodic nature of this radiation burst corresponds to the rotational period of the white dwarf, creating a rhythmic light curve that can be used by astronomers to precisely measure the rotation period of the star. This is an invaluable tool for researchers as it provides a direct link between the behavior of the accreting material and the properties of the white dwarf itself. Interestingly, these periodic variations in brightness often manifest in different wavelengths of light. While the most intense bursts of radiation are typically observed in the X-ray spectrum, these systems can also emit radiation across a wide range of wavelengths, from ultraviolet to optical light. The multi-wavelength nature of these emissions is a hallmark of polars and intermediate polars and provides a unique opportunity to study the behavior of matter under extreme conditions. By observing these systems across different wavelengths, astronomers can gain a more complete understanding of the accretion process and the physics that governs it. The study of polars and intermediate polars also offers insights into the long-term behavior and evolution of binary systems. These systems are dynamic, constantly changing over time as the interaction between the white dwarf and its companion star evolves. As the binary system ages, the companion star may lose mass due to the accretion process, gradually reducing its size and altering the dynamics of the system. In some cases, the white dwarf may even begin to gain enough mass to become unstable and undergo a transformation into a neutron star, or in more extreme cases, collapse into a black hole. Understanding the fate of these systems is critical for understanding the broader picture of stellar evolution and the life cycle of stars and binary systems. The evolution of these systems can also give us clues about the origin of magnetic fields in other astrophysical contexts. Magnetic fields are not unique to polars and intermediate polars. In fact, they are found in a wide range of celestial objects, from planets and stars to galaxies and the interstellar medium. Understanding the role of magnetic fields in these systems can help us understand their role in other environments, such as how they influence the behavior of stars and stellar clusters, the dynamics of the solar wind, and the formation of planetary magnetic fields. In particular, one of the intriguing aspects of studying the magnetic fields in polars and intermediate polars is the possibility that these fields may be connected to the process of stellar nucleosynthesis. While the magnetic fields in white dwarfs are not strong enough to directly influence the fusion reactions occurring in their cores, there is evidence to suggest that the magnetic environment of these stars could play a role in the evolution of heavier elements in the star's interior. As the white dwarf accretes material from its companion star, the magnetic field may affect the distribution of elements within the star, altering the path that the star follows in its evolutionary journey. In addition to this, polars and intermediate polars also hold the potential to reveal more about the behavior of exotic forms of matter under extreme conditions. In particular, the strong magnetic fields present in these systems could lead to the formation of unusual states of matter, such as superconductivity or magnetized plasmas. The interplay between these states of matter and the accreting material could produce phenomena that are not seen in more conventional astrophysical systems, providing researchers with valuable clues about the nature of matter at extreme temperatures and densities. The study of polars and intermediate polars also sheds light on the role of stellar winds in the evolution of binary systems. Stellar winds are streams of charged particles that are emitted by stars as they age. In many binary systems, the winds from one star can interact with the material from its companion, leading to a variety of effects. In polars and intermediate polars, the interaction between the wind from the companion star and the accreting material is significantly influenced by the magnetic fields of the white dwarf. The strength and direction of the wind, along with the shape. What's particularly fascinating about these systems is that the magnetic fields at play can sometimes lead to highly dynamic behavior. For instance, as the white dwarf's magnetic field interacts with the material from its companion star, it can create turbulence in the accretion flow. This turbulence can lead to complex patterns in the radiation emitted by the system, causing flares of various intensities that occur on timescales ranging from seconds to days. The variability in the intensity of these flares is not random, but is instead governed by the intricate interactions between the magnetic field and the accreting material. As astronomers continue to observe these fascinating systems, they are likely to uncover even more surprises. One of the most exciting possibilities is that polars and intermediate polars may hold clues to understanding the formation of more exotic objects in the universe. For example, as the white dwarf in a binary system undergoes a process of accretion, it may gain enough mass to eventually collapse into a neutron star or a black hole. The transition from a white dwarf to a neutron star or black hole is an area of active research, and studying the behavior of polars and intermediate polars could provide important insights into this process. The study of these systems could also play a key role in understanding the overall behavior of matter in extreme environments. The accretion processes that occur in polars and intermediate polars are governed by the interplay between gravity, magnetic fields, and the motion of matter. By studying these processes in detail, scientists may be able to develop better models of how matter behaves under extreme conditions, which could have applications not only in astrophysics but also in other fields such as nuclear physics, plasma physics, and materials science. Ultimately, the strange behavior of polars and intermediate polars offers a glimpse into the heart of some of the most extreme and fascinating processes in the universe. The interactions between magnetic fields, accretion flows, and compact objects are some of the most complex and intriguing phenomena in astrophysics, and studying them can help us unravel the mysteries of how stars evolve, how binary systems behave, and how the fundamental forces of nature shape the cosmos. By continuing to explore these systems, we not only expand our understanding of these unique binary systems, but we also push the boundaries of knowledge, revealing the intricate and often bewildering ways in which the universe operates. The mysteries of polars and intermediate polars are far from being solved, and as we continue to learn more, we may one day unlock the secrets of some of the most enigmatic phenomena in the cosmos. As we continue to unravel the mysteries of polars and intermediate polars, it's essential to explore their broader implications in the context of astrophysical research. These unique binary systems have shown us just how dynamic and complex the universe can be, and by diving deeper into their structure and behavior, we gain insight into not only white dwarfs but also the more general principles that govern stellar interactions in extreme environments. These systems are excellent laboratories for studying the fundamental physics of magnetized, accreting stars, and the knowledge gained from them can be applied to other, more widely known astrophysical phenomena. The study of these systems plays a critical role in understanding stellar magnetism, one of the less understood areas of astrophysics. We know that magnetic fields are common in stars, but the exact mechanisms by which they form and evolve remain a puzzle. While it is well established that magnetic fields are generated by dynamo processes, the precise behavior of these fields in white dwarfs and their role in the evolution of the stars is still an ongoing investigation. One particularly exciting line of research in this area involves the idea that the magnetic fields in white dwarfs might be much more complex than previously thought. Instead of being simple dipole fields, they may have intricate structures that evolve over time. This would have profound implications for our understanding of the magnetic properties of other stars, including neutron stars and even the Sun. Polars and intermediate polars also challenge our understanding of the life cycles of stars and binary systems. These systems are often classified as close binaries because of the intense interaction between the two stars. This interaction typically results in the transfer of mass from the donor star to the white dwarf through a process known as Roche-Lobe overflow. The material from the companion star is pulled toward the white dwarf, forming an accretion disk. The strong magnetic field of the white dwarf then disrupts this disk, funneling the material onto the white dwarf's poles. This interaction is violent, leading to the release of enormous amounts of energy in the form of X-rays and visible light. The mass transfer in polars and intermediate polars also provides an opportunity to study the long-term evolution of binary systems. These systems evolve through various stages, from close binaries to detached systems, and the magnetic field of the white dwarf plays a significant role in this transformation. For instance, as the white dwarf accretes material from its companion, it gradually gains mass. In certain cases, this mass accumulation can lead to the ignition of a thermonuclear explosion on the surface of the white dwarf, leading to a nova event. This process not only affects the white dwarf but also the companion star, which may experience mass loss due to the intense radiation from the nova explosion. Over time, the dynamics of the system change, and the star's orbits may become more circular, eventually leading to the formation of an isolated white dwarf. By studying polars and intermediate polars, astronomers are also learning more about the role of angular momentum in binary star systems. The transfer of angular momentum between the two stars can significantly alter the orbital characteristics of the system. In particular, as the white dwarf accretes mass, it can increase the system's angular momentum, causing the orbit to expand. Conversely, as the system loses mass due to the accretion process, it can lead to a shrinking orbit. These changes in the orbital parameters are not just theoretical, they are observable in real time, making these systems invaluable for testing predictions of stellar dynamics. The study of angular momentum transfer in these systems also has broader implications for understanding the evolution of other binary systems, including those that contain more massive stars, neutron stars, and even black holes. One fascinating aspect of polars and intermediate polars is the way in which the material from the companion star behaves as it interacts with the white dwarf's magnetic field. The magnetic field forces the accreting material into a narrow funnel that accelerates it toward the white dwarf's poles. As the material falls, it heats up to incredibly high temperatures, reaching millions of degrees in some cases. This causes the material to emit large amounts of radiation, particularly in the X-ray spectrum. The intense radiation emitted by the accreting material is one of the defining characteristics of polars and intermediate polars, making them easy to spot in X-ray surveys of the sky. However, it is not just the X-rays that make these systems fascinating. The behavior of the accreting material in the presence of the white dwarf's magnetic field also leads to interesting phenomena such as cyclotron emission, where the electrons in the material spiral along the magnetic field lines, emitting radiation as they do so. This process can produce distinctive signatures in the electromagnetic spectrum, allowing astronomers to study the properties of the magnetic field and the accreting material in great detail. Moreover, this interaction between the magnetic field and the accreting material can lead to the formation of complex structures in the accretion flow. In some systems, the accretion flow becomes highly structured, with the material forming accretion curtains that fall onto the white dwarf's poles in a non-uniform pattern. These structures are often unstable and can vary in intensity, leading to flickering or pulsations in the system's light curve. In intermediate polars, these flickers can occur on timescales ranging from seconds to minutes, providing valuable information about the dynamics of the accretion process. The periodic nature of these variations can help astronomers measure the rotation rate of the white dwarf and the size of its magnetic field. In some cases, the flickering can also reveal information about the properties of the companion star, such as its mass and radius, as well as the orbital parameters of the system. This intricate relationship between the white dwarf's magnetic field and the accretion flow highlights the dynamic and ever-changing nature of these systems. Polars and intermediate polars are not static objects. They are constantly evolving as material is accreted onto the white dwarf and as the binary system undergoes changes in its mass, angular momentum, and orbital characteristics. This variability makes them ideal systems for studying the time-dependent behavior of stars and accretion disks. By observing these systems over long periods of time, astronomers can track the changes in their light curves and identify long-term trends that provide insights into the evolution of the system. The study of polars and intermediate polars also touches on the field of high-energy astrophysics. The intense radiation emitted by these systems can be a valuable tool for studying the physical properties of the white dwarf, the companion star, and the accretion flow. The X-rays produced by the system carry information about the temperature and density of the material in the accretion disk, as well as the strength of the magnetic field. By analyzing the spectra of these X-rays, astronomers can gain insight into the composition of the accreting material and the nature of the interactions between the white dwarf and the companion star. This makes polars and intermediate polars important targets for high-energy observatories such as the Chandra X-ray Observatory and the XMM Newton satellite. As we continue to study these enigmatic systems, we also gain a deeper understanding of the broader phenomena of stellar accretion and magnetism. The processes that occur in polars and intermediate polars are not unique to these systems alone. Similar processes are thought to occur in other systems, including X-ray binaries, cataclysmic variables, and even active galactic nuclei. The insights gained from studying these systems can therefore be applied to a wide range of astrophysical contexts, helping to improve our understanding of the behavior of matter in extreme environments. Ultimately, polars and intermediate polars offer us a unique glimpse into the complex and often mysterious interactions between stars, magnetic fields, and accreting material. As we continue to explore these systems and uncover their secrets, we are not just learning about white dwarfs or binary systems. We are gaining a deeper understanding of the very forces that govern the universe itself. The exploration of polars and intermediate polars does not stop at understanding the interactions between magnetic fields and accreting material. These systems also offer us a deeper look into the nature of stellar death and the ultimate fate of stars. As binary systems, polars and intermediate polars can help to illustrate the evolutionary pathways that stars follow, particularly in their final stages. While we often associate stellar death with the dramatic events surrounding supernovae, white dwarfs provide a different perspective on the end of a star's life. White dwarfs are the remnants of stars that were not massive enough to end their lives in supernova explosions. Instead, these stars shed their outer layers, leaving behind a dense, hot core that eventually cools and fades over billions of years. The intriguing aspect of polars and intermediate polars lies in how these remnants interact with companion stars, often giving them new life in a sense. As we've seen, the intense gravitational and magnetic interactions between the white dwarf and its companion star lead to the accretion of material onto the white dwarf. This not only provides a unique opportunity to study accretion processes, but also offers a chance to understand how white dwarfs evolve under such extreme conditions. The mass transfer in these systems is not a one-way street. The companion star also undergoes changes due to the accretion process. As material is pulled from the companion star, its mass decreases, and it may be subjected to radiation that alters its properties. Over time, this transfer of mass can result in significant changes to the companion star, potentially leading to a complete stripping of its outer layers or even causing the companion to evolve into a white dwarf itself. This dynamic interaction adds a fascinating layer to the study of stellar evolution, particularly in the context of binary star systems. In intermediate polars, the accretion rate is often higher than in polars, which can lead to more dramatic changes in the system. The higher accretion rates can cause the white dwarf to gain mass at a faster rate, and this can trigger different phases of stellar activity. Some intermediate polars may even experience the phenomenon of a nova, a powerful explosion that occurs when accumulated material on the surface of the white dwarf undergoes a thermonuclear reaction. While the specifics of nova explosions in these systems are still not fully understood, they provide an exciting avenue for future research. These outbursts offer an opportunity to study the thermonuclear processes that occur when white dwarfs accumulate enough matter to trigger such violent events. Understanding these explosions is crucial, as they could shed light on the ultimate fate of white dwarfs in close binary systems. Will they continue to accumulate mass until they explode in a supernova-like event, or will they simply cool down over time into a dark, inert remnant? The role of magnetic fields in these systems is also key to understanding their ultimate fate. The magnetic fields in polars and intermediate polars are not just passive actors in the accretion process. They actively shape the evolution of the system. In some cases, the magnetic field of the white dwarf can prevent the accretion disk from forming entirely. Instead, the magnetic field funnels the material directly onto the poles of the white dwarf. This has profound implications for the thermal structure of the system, as the white dwarf's poles become much hotter than the rest of the surface due to the concentrated flow of material. These localized hotspots provide unique opportunities to study the behavior of material at extremely high temperatures and densities, as well as the interactions between the magnetic field and the accreting material. Moreover, the magnetic field can also affect the spin of the white dwarf itself. As material is funneled onto the poles, it can exert a torque on the white dwarf, causing it to spin more rapidly. This spin-up process is particularly important in the context of intermediate polars, where the magnetic field is not strong enough to lock the white dwarf into a synchronous rotation with the orbital period. Instead, the white dwarf in an intermediate polar may gradually spin up over time, eventually reaching extremely high rotation rates. The study of these spin-up processes can provide valuable information about the magnetic field structure of the white dwarf, as well as the long-term evolution of the system. It also offers an opportunity to investigate the physics of magnetically driven accretion in even more extreme settings. As we continue to study the strange behavior of polars and intermediate polars, we also expand our understanding of other types of astronomical phenomena that share similarities with these systems. For example, the study of cataclysmic variables, binary systems where one star is a white dwarf, has been closely linked to the study of polars and intermediate polars. Many of the processes observed in these systems, such as accretion and magnetic interaction, are common to cataclysmic variables as well. This means that by studying polars and intermediate polars, we are not just learning about these specific systems. We are also gaining insights that can be applied to a broader class of objects in the universe. One area of overlap between polars and intermediate polars and other types of stars is the study of X-ray binaries. In these systems, a compact object such as a black hole or neutron star accretes material from a companion star. The physical processes that govern the accretion flow in X-ray binaries are similar to those in polars and intermediate polars, albeit on a much more extreme scale. However, the similarities between these systems highlight the universal nature of accretion and the role that magnetic fields play in shaping the behavior of accreting objects. By studying polars and intermediate polars, astronomers can develop models of accretion that can be applied to a wide range of systems, from white dwarfs to neutron stars to black holes. The study of polars and intermediate polars also opens up exciting possibilities for future research. As technology advances, astronomers will be able to observe these systems in even greater detail, using instruments such as the James Webb Space Telescope and other next-generation observatories. These instruments will allow scientists to study the magnetic fields, accretion processes, and other physical characteristics of polars and intermediate polars with unprecedented precision. This will undoubtedly lead to new discoveries and a deeper understanding of these fascinating systems. In the coming years, we may also uncover new subclasses of polars and intermediate polars that challenge our current understanding of these systems. Just as we have discovered variations in the magnetic fields and accretion behavior of these systems, there is always the possibility that we will encounter new types of stellar interactions that defy our expectations. These surprises are what make the study of polars and intermediate polars so exciting and rewarding. Every new discovery brings us one step closer to unraveling the mysteries of the universe and understanding the complex processes that govern the lives of stars. We are reminded of how much there is still to learn. These systems are far from fully understood, but the insights we have gained so far provide a rich and fascinating tapestry of knowledge about the forces that shape the cosmos. By continuing to study these enigmatic systems, we not only unlock the secrets of white dwarfs and their companions but also gain a deeper understanding of the fundamental processes that govern the behavior of matter in the universe. Through the ongoing research and exploration of these systems, we come to realize just how interconnected everything is in the cosmos. From the smallest white dwarf to the most massive black hole, the forces at play are often governed by the same fundamental principles: accretion, magnetism, angular momentum, and radiation. Each discovery, whether it's about the behavior of polars, the mysteries of intermediate polars, or the nature of stellar evolution, adds a new piece to the puzzle of the universe. As the understanding of polars and intermediate polars deepens, so too does our comprehension of their potential to illuminate other cosmic phenomena. The magnetic fields that dominate these systems not only reveal the intricate mechanisms of accretion but also provide a window into the broader magnetic dynamics that govern the universe. In fact, the study of polars and intermediate polars offers more than just a glimpse into the life cycles of stars. It allows us to probe the interplay between magnetic fields and matter in environments that are extreme by any standard. One of the most compelling aspects of studying these systems is the way that polars and intermediate polars challenge conventional wisdom about the behavior of matter under extreme conditions. For example, the magnetic fields in these systems can become so strong that they warp the very fabric of space and time around them. This isn't just an academic curiosity, it's a direct consequence of Einstein's theory of general relativity, which tells us that the presence of mass and energy causes spacetime to bend. In the case of polars and intermediate polars, the intense magnetic fields can distort the paths of particles, causing them to move in ways that defy our expectations. These systems provide the ideal environment for testing fundamental theories of physics. For example, scientists can observe how matter behaves as it interacts with magnetic fields that are orders of magnitude stronger than any field we encounter on Earth. In these extreme environments, the behavior of matter is governed by the laws of magnetohydrodynamics, MHD, a complex field of study that blends the principles of magnetism and fluid dynamics. MHD models are essential for understanding the flow of matter in systems like polars and intermediate polars, and by refining these models, scientists can develop a better understanding of everything from star formation to black hole accretion. Moreover, the study of polars and intermediate polars can provide crucial insights into the behavior of exotic states of matter. In these systems, matter exists under such extreme conditions that it can take on unusual forms. For instance, the material that is pulled onto the white dwarf's surface can become so hot and dense that it enters a state known as degenerate matter. This form of matter occurs when the electrons in atoms are packed so tightly that they resist further compression, resulting in a very different physical behavior than what we observe in more familiar states of matter. Understanding how matter behaves in these exotic states is key to our understanding of the fundamental properties of matter in the universe, and systems like polars and intermediate polars are ideal laboratories for this kind of research. Additionally, there's another fascinating aspect to the study of polars and intermediate polars that deserves attention: the possibility that these systems may contribute to our understanding of gravitational waves. Gravitational waves are ripples in space-time caused by massive objects, like black holes and neutron stars, moving through space. While we typically associate gravitational waves with these heavier objects, polars and intermediate polars may also play a role. As the white dwarf spins and accretes material from its companion, it generates changes in the system's gravitational field. These small but detectable disturbances could, in theory, contribute to the gravitational wave signal that has already been detected in other parts of the universe. This remains an area of active research, and as gravitational wave observatories continue to improve, we may one day be able to detect gravitational waves originating from systems like polars and intermediate polars. What makes these systems even more intriguing is their potential to evolve into other exotic stellar objects. For example, if a white dwarf in a polar system accumulates enough mass over time, it could eventually reach a critical mass and explode as a type of nova or even transition into a neutron star or black hole. While the specific mechanisms that trigger these events are still being studied, the possibility of observing such dramatic transformations in real time is one of the most exciting prospects for future research. As technology continues to improve, astronomers may be able to observe these systems at much higher resolutions, unveiling more secrets about the violent and dynamic processes at play. Even more tantalizing is the potential for discovering new types of binary systems that fall into the same category as polars and intermediate polars. While these systems are relatively rare, astronomers are constantly on the lookout for new types of interactions between stars that could lead to similar phenomena. With each new discovery, our understanding of the universe grows richer and more complex. Polars and intermediate polars are just the tip of the iceberg when it comes to the bizarre and mysterious interactions that occur between stars, magnetic fields, and matter. There's also the question of how these systems may have contributed to the formation of other structures in the universe. For example, the material that is ejected during nova events in these systems could potentially seed the surrounding space with heavy elements. These elements, in turn, could contribute to the formation of new stars, planets, and other celestial bodies. This process ties into a larger picture of stellar evolution, where each star that explodes, sheds material, or undergoes a transformation can play a role in shaping the future of the universe. By studying these systems, we can gain a better understanding of how the universe recycles material and how stars and planets are born from the remnants of others. As we push the boundaries of what we know about polars and intermediate polars, we also stand at the forefront of new discoveries that could reshape our understanding of the cosmos. The universe is full of mysteries, and systems like these remind us that there is still so much we don't know. The more we study polars, intermediate polars, and similar systems, the more we realize that the universe is far stranger and more complex than we ever imagined. Looking to the future, the continued development of observational technology will play a critical role in unlocking the secrets of these fascinating systems. New space telescopes, ground-based observatories, and advanced computational models will enable scientists to study the dynamics of polars and intermediate polars with greater precision. As our tools improve, so too will our ability to uncover the hidden mechanisms that govern these systems, leading to new breakthroughs in our understanding of stellar evolution, magnetic fields, and the fundamental forces of nature. Ultimately, the study of polars and intermediate polars offers a unique and compelling perspective on the universe. These systems are not only a window into the final stages of stellar evolution, but also a playground for testing some of the most fundamental theories in physics. As scientists continue to investigate these strange and intriguing systems, we will undoubtedly continue to uncover new layers of mystery, deepening our understanding of the universe and the forces that shape it. The magnetic forces, the accretion processes, the transfer of mass, every aspect of these systems is a piece of a much larger puzzle. A puzzle that, when completed, could revolutionize our understanding of the cosmos. Whether it's studying the extreme behavior of matter in magnetic fields, exploring the pathways to nova events, or investigating the role of white dwarfs in the broader stellar ecosystem, the strange behavior of polars and intermediate polars promises to be a central chapter in the ever-evolving story of the universe. As we continue to study the strange behavior of polars and intermediate polars, it's essential to also consider the broader implications that these systems hold for our understanding of other stellar phenomena. The magnetic fields that dominate these systems are not only an intriguing subject of study on their own but also serve as a key to understanding the complex interactions between matter, energy, and magnetic fields in various astrophysical contexts. One of the most fascinating aspects of the research surrounding these binary systems is the connection they provide between the realms of magnetic fields and accretion disks. These processes are fundamental to a variety of cosmic events, from the birth of stars to the formation of black holes. By studying how polars and intermediate polars accrete material from their companion stars, we gain insights into the intricate details of accretion dynamics and the ways in which the material is funneled toward the compact object at the system's core. The magnetic field in polars is so intense that it prevents the material from forming a typical accretion disk. Instead, it is channeled into the magnetic poles of the white dwarf. This phenomenon is part of what gives polars their unique properties. By studying this, scientists can learn more about how magnetic fields influence the flow of matter and other types of binary systems, such as X-ray binaries or active galactic nuclei. In these systems, the interaction of magnetic fields and accreting material can lead to the formation of relativistic jets, another key area of astrophysical research. Intermediate polars offer a fascinating contrast to polars by showing us what happens when the magnetic fields are not as strong. In these systems, the magnetic field is powerful enough to disrupt the formation of a standard accretion disk, but not so intense as in polars. As a result, the material spirals inward in a more complex manner. The dynamics of this material are more difficult to model, but they hold significant potential for understanding the processes that govern accretion in different environments. The interplay between the magnetic field and the accretion process in intermediate polars could help explain some of the complexities observed in other systems, such as neutron star binaries and black hole accretion disks. Additionally, understanding the magnetism of these systems can deepen our understanding of other highly magnetic celestial objects, such as magnetars, neutron stars with magnetic fields 1,000 times stronger than those found in typical neutron stars. Magnetars are known to emit intense bursts of X-rays and gamma rays, and their magnetic fields are thought to be a key factor in these emissions. By comparing polars and intermediate polars to magnetars, researchers can learn more about how magnetic fields evolve and influence the behavior of such extreme objects. What makes this entire field even more exciting is the potential for discovering previously unknown types of systems that exhibit similar behaviors. The universe is vast, and the processes that lead to the formation of binary systems like polars and intermediate polars are not yet fully understood. With each new discovery, astronomers may uncover new subclasses of stars or new types of binary systems that could shed light on the mysteries of stellar evolution, accretion, and magnetism. One potential breakthrough in the study of polars and intermediate polars is the continued improvement of observational techniques, which allows scientists to gather more detailed data. The next generation of telescopes, both ground-based and in space, will provide unprecedented views of these systems. Instruments like the James Webb Space Telescope and the next generation of X-ray observatories will offer new opportunities to observe these fascinating objects in ways that were not previously possible. These observations will help refine our models and offer new insights into the physics of accretion, magnetic fields, and stellar interactions. But even as our technology improves, there are still many unanswered questions about these systems that will require years of study and observation to resolve. For example, we don't yet fully understand the specific mechanisms by which magnetic fields in polars and intermediate polars are generated and maintained. Understanding the origins of these powerful magnetic fields could provide key insights into the processes that occur within white dwarfs and other compact objects. We also don't yet know the full range of behaviors that can arise from different combinations of magnetic field strength and accretion dynamics. Future research may uncover entirely new classes of stellar systems that challenge our current understanding of astrophysics. One of the key areas of interest in the study of these binary systems is the impact that the magnetic fields have on the surrounding environment. In polars, for instance, the strong magnetic field can lead to the formation of powerful outflows, which are streams of charged particles ejected from the white dwarf's magnetic poles. These outflows can have significant effects on the surrounding space environment, potentially affecting the formation of new stars and the dynamics of interstellar matter. By studying these outflows, we can learn more about the role that magnetized winds play in shaping the evolution of galaxies. Similarly, the study of intermediate polars may help us understand the dynamics of accretion in systems where the magnetic field is less dominant. The material being pulled toward the white dwarf behaves differently in these systems than in their more strongly magnetized counterparts. For example, intermediate polars may exhibit unusual patterns of X-ray emissions, and these emissions may vary depending on the angle at which we observe them. By studying these fluctuations, we can learn more about the nature of the accretion process itself and how it is influenced by the strength of the magnetic field. Perhaps one of the most intriguing possibilities in the study of these systems is their connection to gravitational wave research. As mentioned earlier, the binary systems containing white dwarfs, such as polars and intermediate polars, could potentially generate gravitational waves, small ripples in space-time caused by the motion of massive objects. These waves travel across the universe, carrying information about the objects that produce them. Gravitational waves have already been detected from black hole mergers and neutron star collisions, but future observations could reveal the presence of gravitational waves from systems like polars and intermediate polars as well. Detecting gravitational waves from these systems would provide an entirely new way to observe the universe. Unlike light, which can be blocked by dust and gas, gravitational waves can pass through virtually anything, providing a direct probe into the inner workings of these systems. As our detection capabilities continue to improve, it is only a matter of time before we begin to pick up gravitational waves from these fascinating binary systems. The study of polars and intermediate polars also holds promise for advancing our understanding of the ultimate fate of stars. As white dwarfs accrete material and undergo thermonuclear reactions, they can eventually reach a point where they become unstable and explode as novae. These explosions are among the most spectacular events in the universe, and by studying the conditions that lead to nova outbursts in polars and intermediate polars, we can learn more about the processes that govern stellar death. The thermonuclear reactions that occur in these explosions release vast amounts of energy, and the study of these events can provide insights into the end stages of stellar evolution. The possibility of studying these systems in real time, as they evolve and undergo dramatic transformations, adds to the excitement surrounding the research of polars and intermediate polars. Each new observation provides a unique glimpse into the workings of the universe, offering both scientific insights and awe-inspiring phenomena. From the extreme magnetic fields to the complex accretion dynamics, these systems offer a treasure trove of data that could reshape our understanding of the cosmos in the years to come. As we continue to explore the strange behaviors of polars and intermediate polars, we must also consider the technological advances that are helping to drive this research forward. The tools and techniques that scientists use to study these systems have evolved dramatically in recent years, allowing for unprecedented observations and more accurate models. One of the most important advancements has been in the realm of X-ray astronomy. Polars and intermediate polars are known to emit intense X-rays due to the accretion of material onto the white dwarf. These high-energy emissions provide key insights into the physical processes occurring within these systems. X-ray telescopes like the Chandra X-ray Observatory and the Newton satellite have allowed astronomers to study these emissions in great detail, revealing information about the temperature, composition, and structure of the accretion flow. In addition to X-ray telescopes, ground-based observatories are also contributing to the study of polars and intermediate polars. Observatories that focus on optical and infrared wavelengths, such as the Very Large Telescope in Chile, have provided crucial data on the visible light emissions from these systems. By observing these emissions, scientists can track the behavior of the companion star and the interaction between it and the white dwarf's magnetic field. This has helped to build a more complete picture of the dynamics at play in these systems. Another exciting development is the use of radio telescopes to study these systems. While polars and intermediate polars are not typically strong radio sources, some systems have been observed to emit detectable radio waves. These emissions are believed to be linked to the interaction between the magnetic field and the accreting material. By studying these radio emissions, astronomers can learn more about the behavior of the magnetic field and the structure of the accretion flow. Radio observations could also help to identify new polar and intermediate polar systems, expanding our knowledge of these intriguing objects. The increasing availability of data from multiple wavelengths, such as X-ray, optical, and radio, has allowed astronomers to study polars and intermediate polars in greater detail. This multi-wavelength approach is essential for understanding the complex interactions that occur in these systems, as each wavelength provides a unique perspective on the physical processes at work. By combining data from different telescopes, scientists can create more accurate models of these systems, shedding light on the fundamental physics that govern their behavior. In parallel with advancements in observational techniques, the theoretical models of polars and intermediate polars have also made significant progress. For years, researchers have been working to develop models that can explain the behavior of these systems, taking into account the complex interactions between magnetic fields, accretion flows, and radiation. These models are essential for interpreting the observations and predicting the behavior of polars and intermediate polars in different environments. One of the major challenges in modeling these systems is the difficulty of simulating the behavior of the magnetic fields. The magnetic fields in polars and intermediate polars are extremely strong, and they can cause significant distortions in the surrounding matter. The complexity of these interactions makes it difficult to create accurate simulations that can capture all of the nuances of the system. However, recent breakthroughs in computational astrophysics have allowed for the development of more sophisticated models that take into account the intricacies of magnetic accretion and the resulting emissions. As our understanding of polars and intermediate polars continues to grow, we are also gaining new insights into the broader field of astrophysics. These systems serve as a valuable testing ground for theories about the behavior of matter and energy in extreme conditions. For example, the study of the accretion process in polars and intermediate polars can help us better understand the accretion processes that occur in other systems, such as active galactic nuclei and black holes. By understanding the physics of these systems, we can improve our models of other high-energy astrophysical phenomena. In addition to their relevance to astrophysics, polars and intermediate polars also have broader implications for our understanding of the universe as a whole. These systems are important pieces of the puzzle when it comes to understanding the life cycle of stars. The evolution of binary systems like these, where one star has evolved into a white dwarf while the other remains a main sequence star, provides valuable information about the processes that shape the fates of stars. The study of these systems can help us better understand how stars die, how they influence the surrounding environment, and how they ultimately contribute to the chemical enrichment of galaxies. Moreover, these systems offer important clues about the nature of magnetic fields in general. Magnetic fields are a fundamental component of astrophysical objects, from planets and stars to galaxies and black holes. By studying the behavior of the magnetic fields in polars and intermediate polars, we can learn more about the role that magnetic fields play in the evolution of celestial objects and the formation of cosmic structures. The strong magnetic fields in these systems may be a key to understanding the broader magnetism of the universe. Beyond the scientific implications, the study of polars and intermediate polars also has a more philosophical aspect. These systems remind us of the vast and mysterious nature of the cosmos, and how much there is still to learn. Despite decades of research, polars and intermediate polars continue to surprise astronomers with their unexpected behaviors. Each new discovery reveals another layer of complexity in the universe, and it is only through continuous exploration and observation that we will begin to uncover the deeper truths that govern the behavior of these systems. Looking to the future, the study of polars and intermediate polars is likely to continue to be a major area of research in astrophysics. With new telescopes and observatories coming online, scientists will have access to even more detailed data, allowing them to refine their models and make new discoveries. As our observational techniques improve, we will be able to probe these systems more deeply than ever before, uncovering new insights into the nature of white dwarfs, magnetic fields, and accretion processes. Moreover, as our understanding of polars and intermediate polars evolves, we may also find new applications for this knowledge in other fields of science and technology. For example, the study of magnetic fields in these systems could have implications for the development of new materials and technologies that rely on strong magnetic fields, such as in the field of magnetic confinement for nuclear fusion. The lessons learned from these systems could one day lead to advances in energy production and other technologies that benefit society. The study of polars and intermediate polars is not just about understanding a specific class of stellar systems. It is about unlocking the fundamental physics of the universe and uncovering the processes that shape the cosmos. These systems are complex, dynamic, and rich with mystery, and they offer a unique opportunity to explore the universe's most extreme and fascinating phenomena. With each new discovery, we come closer to unraveling the secrets of the stars, the magnetic fields, and the fundamental forces that govern the cosmos. As we continue to investigate polars and intermediate polars, we find that their study is closely tied to the broader exploration of stellar evolution. The nature of these binary systems offers insight not just into the behavior of white dwarfs and their magnetic fields, but into the larger mechanisms that govern the life cycle of stars. White dwarfs are remnants of low to medium mass stars that have exhausted their nuclear fuel and shed their outer layers. What remains is a dense, Earth-sized core composed mainly of carbon and oxygen. However, the role of magnetic fields in the evolution of white dwarfs is still an area of active research. While many white dwarfs have magnetic fields, those in polars and intermediate polars exhibit some of the most extreme examples of this phenomenon. The interaction between the magnetic field of the white dwarf and the accreting material from the companion star leads to some of the most fascinating and unusual behaviors observed in these systems. The magnetic field of a white dwarf in a polar system is typically incredibly strong, on the order of 1,000,000 times stronger than Earth's magnetic field. This intense field governs the motion of the accreted material, forcing it to follow magnetic field lines and creating a hot, highly concentrated region of accretion. This concentrated accretion leads to X-ray emissions, which are often the most prominent feature of polars and intermediate polars. In intermediate polars, the accretion flow does not align perfectly with the magnetic field, leading to more complex interactions. These differences in the geometry of the accretion flow result in distinct observational signatures, including changes in brightness and periodic variability in X-ray emissions. In fact, the variability in the light emitted by polars and intermediate polars is one of the most intriguing aspects of these systems. The accretion of material onto the white dwarf in these systems is not a continuous process. Instead, it often occurs in bursts, or in a highly variable fashion. This periodic variability can be attributed to the way the magnetic field channels the accreting material onto the white dwarf's surface. In some cases, this process is highly regular, with the periodicity of the bursts corresponding to the rotation period of the white dwarf. In other cases, the variability is more chaotic, with bursts occurring at irregular intervals. The study of this variability provides crucial insights into the physical processes occurring within these systems and helps astronomers understand the nature of the accretion flow and the role of the magnetic field. Additionally, polars and intermediate polars are also important for understanding the relationship between mass transfer and the evolution of binary systems. In a polar system, the white dwarf's strong magnetic field significantly alters the nature of the mass transfer process. The accreting material is funneled onto the white dwarf's magnetic poles, where it can accumulate and generate intense heat, often reaching temperatures of millions of degrees. This process leads to the emission of X-rays, as previously mentioned, and can also cause the material to undergo significant shock heating, further increasing the energy output. In intermediate polars, the magnetic field is still strong, but the accretion flow is not fully aligned with the magnetic poles. Instead, the material tends to form an accretion disk around the white dwarf before being funneled onto the poles. This results in a different pattern of X-ray emissions, and the behavior of the system is often more complex. The periodicity of the X-ray bursts in intermediate polars is typically linked to the rotation of the white dwarf, although the relationship between the two can sometimes be more difficult to interpret due to the complex geometry of the accretion flow. As we deepen our understanding of the accretion processes in these systems, we also gain insight into the broader implications for the study of compact objects. White dwarfs, neutron stars, and black holes are all examples of compact objects, remnants of stars that have undergone significant gravitational collapse. The study of polars and intermediate polars helps astronomers understand how accretion processes operate in these extreme environments, providing a model for the behavior of matter in other systems, such as active galactic nuclei and the accretion disks around supermassive black holes. Moreover, the study of magnetic fields in polars and intermediate polars is particularly relevant for understanding the role of magnetism in the evolution of compact objects. Magnetic fields are a fundamental feature of these objects, and they play a key role in shaping the way matter is accreted onto the surface of these stars. Understanding the behavior of these magnetic fields is crucial not only for studying individual systems but also for understanding how they influence the broader evolution of galaxies and other cosmic structures. The peculiar behaviors of polars and intermediate polars also provide a unique window into the complex relationship between stars and binary systems. In these systems, one star is typically a main sequence star or red giant, and the other is a compact object, a white dwarf. The interaction between these two stars is governed by the process of mass transfer, where material from the companion star is siphoned off and accreted onto the white dwarf. The presence of the magnetic field in polars and intermediate polars makes this process much more dynamic, as it strongly influences the way the material is funneled onto the white dwarf. This interaction can lead to a number of interesting phenomena, such as the formation of accretion disks and the generation of powerful radiation. The fact that these systems often exhibit such dramatic variations in their X-ray output makes them particularly valuable for astronomers studying the behavior of matter in extreme conditions. The study of polars and intermediate polars, in turn, helps scientists understand the broader context of stellar evolution, the formation of compact objects, and the role of binary interactions in the development of stellar systems. Furthermore, these systems offer crucial insights into the potential end states of stars. When a white dwarf in a binary system accretes enough material, it may eventually undergo a catastrophic event known as a nova. Novae are explosive events that occur when a white dwarf accretes material from its companion star, leading to a runaway thermonuclear reaction on the surface of the white dwarf. This explosion causes the star to brighten significantly, often by several magnitudes. Polars and intermediate polars may eventually evolve into nova systems, where the accumulated material reaches the point of ignition. Understanding the behavior of these systems and the accretion process is crucial for predicting when and how nova events might occur. In addition to their relevance to stellar evolution, polars and intermediate polars also have broader implications for our understanding of astrophysical phenomena. The study of these systems is helping to refine our understanding of the processes that govern the dynamics of compact objects, magnetic fields, and accretion flows. As new data from telescopes and observatories continues to be collected, our understanding of these systems will continue to evolve, revealing new insights into the nature of the universe and the behavior of matter in extreme environments. As we continue our investigation into the strange behavior of polars and intermediate polars, one fascinating aspect of these systems is how they continue to challenge our understanding of stellar physics. While we have made tremendous strides in understanding the fundamental processes at play within these systems, there are still many unanswered questions that keep astronomers and astrophysicists intrigued. One of the most persistent mysteries involves the exact mechanisms behind the accretion of material onto the white dwarf. In both polars and intermediate polars, material is funneled from the companion star towards the white dwarf. However, the complex interaction between the magnetic fields of the white dwarf and the accreting material remains elusive. This interaction is not just a simple matter of material being pulled toward the white dwarf by gravity. Instead, it involves a highly dynamic process influenced by the magnetic field's strength, orientation, and structure. In polars, the magnetic field is so strong that it forces the accreting material to move along specific pathways dictated by the field lines. This produces a highly concentrated flow of material onto the poles of the white dwarf, where the material then undergoes shock heating, producing X-rays and other high-energy radiation. In intermediate polars, the accretion is less tightly controlled by the magnetic field, leading to a more complex flow of material. The accreting material can form an accretion disk around the white dwarf, which interacts with the magnetic field in a less predictable manner. This leads to differences in the observed behavior of polars and intermediate polars, particularly in terms of their X-ray emissions. What makes this even more intriguing is the fact that the magnetic field strength in intermediate polars is typically weaker than in polars, yet the behavior of the accreting material can still lead to the formation of strong X-ray sources. This raises the question, how is the accretion process in intermediate polars able to generate such intense radiation despite the weaker magnetic field? One possibility is that the accretion flow in intermediate polars might be more chaotic, leading to a less stable and more fluctuating environment. This could produce more extreme heating and greater X-ray emissions, despite the field's relative weakness. Another compelling mystery centers around the role of the companion star in these systems. In most cases, the companion star in a polar or intermediate polar system is a low-mass star, typically a red dwarf or a late-type main sequence star. These stars are much cooler and less luminous than the white dwarf, yet they play a crucial role in supplying the material that is accreted onto the white dwarf. The process of mass transfer from the companion star to the white dwarf is influenced by several factors, including the orbital configuration of the system, the magnetic field of the white dwarf, and the presence of any additional elements, such as gas clouds or accretion disks. In intermediate polars, the relationship between the two stars is even more complex. The companion star's material is not simply siphoned off by the white dwarf's magnetic field, as in polars. Instead, an accretion disk is often formed, with material moving in spirals around the white dwarf. This adds another layer of complexity to the system, as the accreting material is subject to both gravitational forces and magnetic forces, which can create a highly turbulent environment. The result is that intermediate polars tend to exhibit more complex and varied behaviors compared to polars, with a wider range of X-ray variability and different emission patterns. Yet another intriguing question involves the evolution of these systems over time. How do polars and intermediate polars evolve, and what do their changes tell us about the fate of binary systems in general? Over time, the magnetic fields of white dwarfs can weaken or change in structure, which may alter the way material is accreted onto the star. The accretion process itself can also lead to changes in the system's dynamics, potentially causing the system to evolve into a nova, where a sudden and dramatic burst of energy is released. There is also the question of how the system's orbital parameters, such as the orbital period and the mass transfer rate, affect its long-term evolution. Some systems may evolve into cataclysmic variables, which are a type of binary system in which the material from the companion star is accreted onto the white dwarf in a highly unstable and explosive manner. This process can lead to the formation of novae or even type I supernovae, which are thought to result from the thermonuclear explosion of a white dwarf. Understanding the behavior of polars and intermediate polars is crucial for understanding these processes and predicting the future of other types of binary systems. An exciting aspect of studying these systems is that they offer a unique laboratory for testing our theoretical models of accretion and magnetic fields. Polars and intermediate polars allow astronomers to study how magnetic fields can affect the flow of material in extreme environments. They also provide valuable data on how material behaves when subjected to intense magnetic forces, temperatures, and radiation fields. As such, these systems help refine our understanding of the broader principles of stellar evolution, accretion processes, and the role of magnetic fields in shaping the dynamics of compact objects. Another key point to consider is the potential for multi-wavelength observations of polars and intermediate polars. While X-ray emissions are the most prominent feature of these systems, they also emit across other parts of the electromagnetic spectrum, including optical, ultraviolet, and radio wavelengths. Studying these emissions in conjunction with X-ray data can provide a more comprehensive understanding of the behavior of these systems. For example, optical observations can reveal details about the companion star and the accretion disk, while ultraviolet observations can help scientists understand the high-energy processes occurring close to the white dwarf. Radio observations, though less common, can also provide valuable information about the magnetized environment of these systems. The combination of multi-wavelength data and detailed theoretical models is helping astronomers develop a more complete picture of the behavior of polars and intermediate polars. As new observatories and telescopes come online, it is likely that we will gain even deeper insights into these fascinating systems. The upcoming James Webb Space Telescope, for instance, may be able to study the thermal emissions from these systems in unprecedented detail, providing new data on the temperature distribution in the accretion flow and the structure of the magnetic field. In addition, advancements in X-ray astronomy, such as the upcoming XRISM mission, will help refine our understanding of the X-ray emissions from these systems, giving us a more detailed picture of the processes that govern their behavior. Beyond their intrinsic scientific value, polars and intermediate polars also serve as a reminder of the vast and mysterious universe in which we live. These systems are just one example of the many strange and exotic phenomena that await discovery in the cosmos. From the behavior of magnetic fields in compact objects to the dynamics of mass transfer in binary systems, there is still so much to learn about the fundamental forces that shape the universe. As we continue to explore the behavior of polars and intermediate polars, we are not just uncovering the secrets of these specific systems, we are also gaining insight into the larger processes that govern the evolution of stars, the formation of compact objects, and the nature of matter in extreme environments. These discoveries will continue to inspire future generations of astronomers and physicists, pushing the boundaries of our understanding and opening new doors to the mysteries of the cosmos. As we continue exploring the mysteries of polars and intermediate polars, we encounter even more fascinating aspects of these stellar systems. The behavior of these systems extends beyond the X-ray emissions and magnetic interactions we've discussed, touching on the wider context of binary star systems and how they evolve over time. To better understand the unique behavior of these systems, we must first consider the nature of the white dwarf itself. White dwarfs are the remnants of low to medium mass stars that have exhausted their nuclear fuel. As these stars reach the end of their lives, they shed their outer layers, leaving behind a dense, hot core. This core, known as the white dwarf, is composed mostly of electron-degenerate matter, a state of matter in which the electrons are packed so closely together that they resist further compression. White dwarfs are incredibly dense, with masses comparable to the Sun, but sizes similar to Earth. Their small size leads to extremely high surface gravity, which plays a key role in how these stars interact with their companion stars and binary systems. In polars and intermediate polars, the white dwarf is typically the more massive and compact object in the system. The companion star, on the other hand, is much less massive, usually a red dwarf or another low-mass star. These companion stars are often close enough to the white dwarf that material is transferred from the companion star to the white dwarf through a process called Roche lobe overflow. This occurs when the companion star's outer layers expand beyond its Roche lobe, a region defined by the gravitational influence of the white dwarf. Once the companion star's material crosses this boundary, it is pulled toward the white dwarf, where it is subject to the white dwarf's intense magnetic field. However, what sets polars and intermediate polars apart from other cataclysmic variables is the role of the white dwarf's magnetic field. In both types of systems, the magnetic field of the white dwarf is incredibly strong, but the way this field interacts with the accreting material differs between polars and intermediate polars. In polars, the magnetic field is strong enough to disrupt the formation of an accretion disk. Instead, the material from the companion star is funneled directly onto the poles of the white dwarf. This creates a highly focused flow of material that collides with the white dwarf's surface, generating significant amounts of heat and radiation. This accretion process produces intense X-rays and optical emissions, which can be observed from Earth. The process of material being funneled onto the poles also leads to the formation of large, localized hot spots on the white dwarf's surface. These hot spots emit radiation that can be detected in different wavelengths, providing valuable information about the nature of the accretion process. In contrast, intermediate polars have a weaker magnetic field, which allows the formation of an accretion disk around the white dwarf. However, the magnetic field still plays a crucial role in the accretion process, as it can disrupt the inner part of the accretion disk. In some cases, the magnetic field can channel material from the inner regions of the disk onto the poles of the white dwarf, similar to what happens in polars, but in a less orderly manner. The result is that intermediate polars exhibit more complex and varied behavior, with X-ray emission that is less steady and more erratic than in polars. This variation in behavior between polars and intermediate polars is a major point of interest for astronomers. It challenges our understanding of how accretion occurs in the presence of a magnetic field and how the strength of the field influences the overall dynamics of the system. While polars tend to have relatively simple, steady X-ray emissions, intermediate polars show much more variability in their X-ray light curves. This variability can be attributed to the chaotic nature of the accretion process in intermediate polars, where the material is less tightly controlled by the magnetic field. The variability of intermediate polars is not just a minor detail, it provides valuable insights into the nature of accretion itself. By studying the X-ray light curves of these systems, astronomers can learn more about the structure of the accretion disk, the nature of the magnetic field, and the overall dynamics of the material as it spirals toward the white dwarf. This kind of detailed study is only possible because of the unique properties of these systems, which allow astronomers to observe accretion processes in real time. One of the key features of both polars and intermediate polars is the presence of strong X-ray emissions, which are a direct result of the accretion process. These X-rays are produced when the material falling onto the white dwarf is compressed and heated to extremely high temperatures. As the material collides with the white dwarf's surface, it generates shock waves that produce X-ray radiation. This high-energy emission is one of the defining characteristics of these systems, and studying it allows astronomers to gain insights into the accretion process itself, as well as the conditions around the white dwarf. The study of X-ray emissions from polars and intermediate polars is made possible by a variety of X-ray observatories, including the Chandra X-ray Observatory and the XMM Newton satellite. These observatories allow scientists to observe the high-energy radiation emitted by these systems and study the detailed properties of the X-ray spectrum. The X-ray data can reveal crucial information about the temperature and density of the accreting material, as well as the geometry of the accretion flow. By analyzing these X-ray emissions, astronomers can better understand how material behaves as it falls toward the white dwarf and how the magnetic field influences the accretion process. Another key aspect of these systems is the impact of the magnetic field on the material as it accretes onto the white dwarf. The magnetic field of the white dwarf is not static. It can evolve over time, influencing the way material is accreted. In some cases, the magnetic field may become more concentrated in certain regions, leading to the formation of strong accretion funnels. These funnels direct the material onto the poles of the white dwarf, where it undergoes shock heating and generates X-rays. The evolution of the magnetic field can also affect the overall structure of the system, potentially altering the way the accretion disk behaves or the intensity of the X-ray emissions. As we continue to study these fascinating systems, it becomes clear that polars and intermediate polars offer a unique opportunity to explore the complex interactions between magnetic fields, accretion disks, and compact objects. These systems provide valuable insights into the fundamental processes that govern the behavior of matter in extreme environments, and their study continues to reveal new and unexpected results. As new technologies and observatories come online, we can expect even more detailed observations and groundbreaking discoveries that will deepen our understanding of these strange and mysterious systems. The ongoing study of polars and intermediate polars is not only advancing our knowledge of stellar systems, but also contributing to our understanding of the universe as a whole. These systems serve as a reminder of the incredible diversity and complexity of the cosmos, where even the smallest and most compact objects can reveal the deepest mysteries of physics. As we continue to explore these systems, we will no doubt uncover new secrets about the nature of stars, accretion, magnetic fields, and the fundamental forces that shape the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.